Look up at the night sky. What do you see? A tapestry of stars, stretching across the darkness. Countless points of light, some belonging to our own galaxy, others representing entire galaxies so distant that their light has traveled for millions of years to reach your eyes. This cosmic panorama tells a story of abundance, a universe filled with matter, energy, and endless celestial bodies. But between those stars and galaxies lies something else, something we often overlook: space itself, the vast emptiness that cradles all of existence. We tend to focus on what is there, rather than what is not. Yet in astronomy, nothingness can be just as significant as somethingness. Imagine floating through our universe, past stars and nebulae, beyond our Milky Way, out into the deep cosmic ocean where galaxies themselves appear as mere islands in an endless sea. As you travel, you would notice that these galaxies are not distributed randomly. They form patterns, clusters, networks, and walls, creating what astronomers call the cosmic web. This vast structure resembles a sponge, with dense regions where galaxies congregate, and emptier regions where few galaxies exist at all. These emptier regions are known as cosmic voids. They are the negative space of our universe, the gaps between the cosmic tapestry. Most voids are tens to hundreds of millions of light years across, and they are normal features of our cosmos. Our universe has always had its empty spaces, its cosmic deserts where matter is scarce, and galaxies are few and far between. But tonight, we explore something different, something that challenges our understanding of how the universe should be structured. Something that, according to our best theories and models, should not exist at all. Imagine a region of space so vast that it would take light 1 billion years to cross from one side to the other. For comparison, our entire Milky Way galaxy is roughly 100,000 light-years across. This void is 10,000 times larger, and it is nearly empty, a region where galaxies are not merely rare, but almost entirely absent. A place of such profound emptiness that it has left astronomers questioning fundamental aspects of our cosmological models. This is the story of the greatest emptiness we have ever discovered, a void so large, so empty, that it stands as one of the most perplexing mysteries in modern astronomy. Some call it the supervoid. Others refer to it as the cold spot, after its unusual signature in the cosmic microwave background radiation. Whatever name we give it, this enormous bubble of nothingness represents something extraordinary, something unexpected, something that invites us to reconsider what we know about the universe itself. As you rest and listen, we will journey together into this cosmic anomaly. We will explore how it was discovered, why it puzzles scientists, and what it might mean for our understanding of the cosmos. The story of this void is not merely about emptiness. It is about the boundaries of knowledge, the limits of our theories, and the endless capacity of our universe to surprise us. So close your eyes and imagine the vastness of space. Feel yourself drifting through the stars, toward a region where even stars become scarce, where emptiness reigns, where one of the greatest mysteries of astronomy awaits. This is the billion light-year void that should not exist, and its story is just beginning. As our journey through the billion light-year void comes to a close, we find ourselves returning to the questions that first drew us to this cosmic enigma. What is this vast emptiness in the fabric of the universe? How did it form? What does it tell us about the nature of the cosmos? And what meaning might we find in this enormous absence amid the cosmic tapestry? Throughout our exploration, we have traced the story of the supervoid from its initial detection as an anomalous cold spot in the cosmic microwave background to the ongoing efforts to map its true extent and understand its origins. We have examined the theories that attempt to explain its existence, from statistical flukes to exotic physics, and contemplated the future observations that might finally resolve the mystery. We have even considered what it might be like to live within this cosmic desert, gazing out at a darker, emptier sky than the one we know. This journey has taken us across the vastness of space and the depths of time, from the primordial fluctuations of the early universe to the complex structures of the present-day cosmic web. It has introduced us to the fundamental forces and components that shape our universe, from gravity and dark energy to galaxies and the cosmic microwave background. And it has invited us to ponder not just the physical reality of the supervoid, but its philosophical implications as well. The billion light-year void, like many great scientific mysteries, reveals as much about the process of scientific inquiry as it does about the universe itself. It reminds us that science is not a simple accumulation of facts, but a dynamic, evolving dialogue between theory and observation, between what we think we know and what we actually observe. The supervoid challenges our current understanding, pushing us to refine our theories, improve our observations, and perhaps discover new physics in the process. This challenge is not a failure of science, but its strength. The ability to recognize anomalies, to acknowledge the limits of current understanding, and to pursue new explanations is what drives scientific progress. The supervoid, whether it ultimately proves to be a statistical outlier within the standard cosmological model or evidence for something more exotic, has already made its contribution to this progress by stimulating new observations, analyses, and theoretical explorations. Beyond its scientific significance, the supervoid offers a unique perspective on our place in the cosmos. Human history has been marked by a series of decenterings, as Copernicus showed that Earth is not the center of the solar system, as Hubble demonstrated that our galaxy is just one among billions, and as cosmologists revealed that even ordinary matter makes up only a small fraction of the universe's content. The supervoid adds another layer to this perspective, suggesting that even the cosmic web, that vast network of filaments and clusters that forms the universe's large-scale structure, is primarily characterized by emptiness rather than fullness. Yet this decentering need not diminish us. Rather, it places human existence within a larger context that enriches our understanding and appreciation of being. The fact that conscious beings, capable of discovering and contemplating structures as vast as the supervoid, emerged from the complex interactions of matter and energy in one corner of the cosmos speaks to the remarkable generative potential of the universe. Our ability to comprehend scales and phenomena far beyond our direct experience is itself a kind of transcendence, a reaching beyond our immediate circumstances to engage with the cosmos as a whole. The supervoid also invites us to reconsider our relationship with emptiness and absence. In many human cultures and contexts, emptiness is viewed negatively, as a lack or privation to be avoided or filled. But the cosmic voids, including the supervoid, play an essential role in the universe's structure and evolution. They are not merely absences, but active participants in cosmic dynamics, regions where dark energy dominates and the expansion of space proceeds more rapidly than average. The emptiness between galaxies is as fundamental to the cosmos as the galaxies themselves. This perspective suggests a more balanced approach to emptiness in our own experience. Just as the voids in the cosmic web give definition and structure to the filaments and clusters, the empty spaces and moments in human life can provide context and meaning for our activities and connections. Silence gives form to music, pauses give rhythm to conversation, solitude provides contrast to social engagement. The supervoid, in its vastness and subtlety, reminds us of the value and significance of these forms of emptiness. As we gaze into the cold spot and contemplate the enormous void aligned with it, we are looking not just at an astronomical anomaly, but at a mirror that reflects our own nature and place in the universe. We too exist in the context of vast emptiness, our planet a tiny oasis of life in the immense desert of space. Yet from this seemingly insignificant position, we have been able to detect and study structures billions of light years across, to piece together the history of the cosmos, from its fiery beginning to its accelerating present, and to contemplate its far future. This capacity for comprehension and wonder, for finding meaning in the patterns of the universe, is perhaps the most remarkable feature of our existence. The supervoid, in challenging our understanding and stretching our theoretical frameworks, has contributed to this ongoing process of discovery and reflection. It has enriched our cosmic perspective and deepened our appreciation for the complexity and mystery of the universe we inhabit. As future telescopes and surveys provide new insights into the supervoid and other large-scale structures, our understanding will continue to evolve. The mystery may be resolved, giving way to new questions and challenges, or it may persist, a cosmic enigma that continues to inspire and puzzle astronomers for generations to come. Either outcome represents not an end but a continuation of the scientific journey, a journey that has consistently revealed the universe to be more vast, more complex, and more wondrous than we previously imagined. In this billion light-year void, this greatest emptiness we have yet discovered, we find not meaninglessness, but meaning, not insignificance, but significance. It stands as a testament to the universe's endless capacity to surprise and inspire us, to challenge our understanding and expand our perspective. Like all great scientific discoveries, it has not diminished the wonder of existence, but enhanced it, revealing new dimensions of the cosmic tapestry that we are privileged to contemplate and explore. As you drift towards sleep beneath the canopy of stars, consider that between those points of light lie vast regions of relative emptiness, cosmic voids where galaxies are few and far between. And somewhere among them, spanning a billion light-years of space, lies the supervoid, a cosmic desert of extraordinary scale. In this immense emptiness, we have found not nothing, but something a challenge to our understanding, a window into cosmic evolution, a mirror for philosophical reflection. The void, with its absence of conventional structure, offers a profound silence from which we can better hear the universe's deepest rhythms. In this quiet place in the cosmos, we find space to wonder, to imagine, to dream of the vaster realities that lie beyond our everyday perception. As you sleep, may your mind drift through these cosmic voids, finding in their emptiness not a barren desert but a canvas for possibility, a silence pregnant with potential, a darkness that heightens our appreciation for the light of understanding. In this billion light-year void, as in all great mysteries, we discover not just facts about the universe, but truths about ourselves, our capacity for wonder, our drive to understand, our ability to find meaning even in emptiness. And perhaps, in the end, that is the most valuable insight of all. Having explored the scientific dimensions of the supervoid, from its discovery and mapping to its theoretical implications and the future observations that might unlock its secrets, we now turn to more contemplative terrain. What meaning might we find in this vast cosmic emptiness? How does the existence of immense voids in the universe reflect upon our understanding of ourselves and our place in the cosmos? Emptiness has long been a subject of philosophical and spiritual contemplation across various cultures and traditions. From the concept of shunyata, emptiness, in Buddhist thought to the vacuum of ancient Greek atomists, from the void of existentialist philosophy to the nothingness contemplated in contemporary physics, the idea of emptiness has repeatedly served as a mirror for human reflection on existence itself. The supervoid, as perhaps the largest single empty structure in our observable universe, offers a new focus for these ancient contemplations. Its enormous scala potentially spanning a billion light-years places it beyond human experience or intuition. We cannot truly visualize or comprehend such vastness. We can only approach it abstractly, through mathematics and metaphor. Yet in this abstraction lies an opportunity for wonder and perspective that few other scientific discoveries can match. In a universe of somethingness, nothingness takes on profound significance. The supervoid is not merely an absence, but a presence of its own kind of negative space that helps define the positive features around it. Just as a sculptor might create a form by removing material, revealing the shape hidden within, the cosmic web of filaments and clusters is defined as much by the voids between them as by the structures themselves. The void and the plenum, emptiness and fullness, absence, and presence these complementary aspects together compose the complete picture of our cosmos. This complementarity reflects a pattern found throughout nature, from the atomic to the galactic scale. Atoms are mostly empty space, with tiny nuclei surrounded by vast regions where electrons exist as probability clouds rather than definite objects. Yet from this near emptiness emerges the solidity of matter that constructs our world. Similarly, galaxies consist primarily of the empty space between stars, yet they form coherent, structured systems with distinctive properties and behaviors. And on the largest scales, the cosmic web itself is mostly void, with the filaments and clusters of galaxies defining its structure like threads in a tapestry. The supervoid represents this principle of complementarity at its most extreme region, so empty that it challenges our theories and expectations. Yet it is precisely this extremity that makes it valuable, both scientifically and philosophically. By studying the boundaries of what is possible or expected within our universe, we gain deeper insights into its fundamental nature. The exception illuminates the rule. The outlier reveals the pattern. There is something paradoxical about the supervoid as well. Though nearly devoid of matter, it is full of energy, specifically dark energy, the mysterious force driving the accelerating expansion of the universe. Dark energy, which makes up about 68% of the total content of the cosmos, is distributed uniformly throughout space, including the emptiest voids. So the supervoid, while almost entirely free of galaxies, stars, gas, and dust, is nevertheless permeated by this invisible energy, quietly working to expand the fabric of space-time. This paradox hints at deeper questions about the nature of reality. Is true emptiness, a perfect void, even possible in our universe? Quantum field theory suggests that even the vacuum of empty space is teeming with activity at the subatomic level, as virtual particles continuously pop in and out of existence. The vacuum energy associated with these quantum fluctuations may indeed be related to dark energy itself, though the theoretical calculations don't yet match observational evidence. If so, then the supervoid, despite its apparent emptiness, might be one of the purest expressions of these fundamental quantum processes operating at cosmic scales. The supervoid also invites us to reflect on the nature of observations and the role of perspective in science. We perceive the void as an absence, a region lacking in the galaxies and structures that define the rest of the cosmic web. But this perception depends entirely on what we are looking for and how we are looking for it. If we could somehow observe dark matter or dark energy directly, rather than inferring their presence through their effects on visible matter, the supervoid might appear not as emptiness, but as a vast, subtle pattern of these invisible components of the universe. This consideration reminds us that science itself is limited by our observational techniques and conceptual frameworks. What appears as a void, from one perspective, might be richly structured from another. The history of science is filled with examples of empty spaces, later found to contain previously undetected phenomena, from the discovery of microorganisms in apparently clear water to the recognition of dark matter in the apparently empty space between galaxies. The supervoid may yet hold secrets that will only be revealed by future observational capabilities or theoretical advances. Beyond these philosophical considerations, the supervoid carries poetic resonance as well. There is a kind of cosmic sublime in contemplating emptiness on such an enormous scale. The sublime, as described by philosophers like Immanuel Kant, arises when we encounter something so vast or powerful that it overwhelms our senses and imagination, yet still engages our reason. The supervoid, with its billion light-year expanse, certainly qualifies. We cannot truly visualize it, yet we can think about it, calculate its properties, and wonder at its existence. This sublime quality is enhanced by the void's relationship to the cosmic microwave background and the cold spot. Here we have light from the earliest moments of the universe, traveling for over 13 billion years, bearing the subtle imprint of primordial density fluctuations, then passing through this enormous void and being slightly cooled by its gravitational effects, before finally reaching our telescopes on Earth. The temporal and spatial scales involved are almost beyond comprehension, yet they connect in a coherent narrative that our science can reveal. There is poetry in this connection across cosmic time and space, in this dialogue between the universe's birth and its present structure. The supervoid also offers a potent metaphor for the human condition. We too exist in a kind of cosmic voider planet orbiting an ordinary star in a remote arm of an ordinary galaxy, surrounded by the vast emptiness of intergalactic space. Yet from this seemingly insignificant position, we have been able to discern the structure and history of the entire observable universe. Our intellectual reach extends far beyond our physical presence, allowing us to comprehend scales and phenomena that our bodies could never directly experience. This contrast between our physical limitation and our intellectual expansion mirrors the contrast between the void's emptiness and the rich scientific understanding it has inspired. From absence comes insight, from isolation comes connection. The void, like human consciousness, transcends its local conditions to engage with the cosmos as a whole. There is also a certain comfort to be found in cosmic emptiness. In a universe filled with violent processes, exploding stars, colliding galaxies, matter spiraling into black holes voids, represent regions of relative calm and stability. They are cosmic oases where the density of matter is low, interactions between galaxies are rare, and the expansion of space proceeds more smoothly than in denser regions. If life were to evolve on a planet within the supervoid, it might find this environment more conducive to long-term stability than the tumultuous regions where galaxies cluster together. This perspective invites us to reconsider our relationship with emptiness in our own lives and experiences. Western culture, particularly in its modern consumerist manifestation, often treats emptiness as something to be avoided, or filled empty time should be occupied with activity. Empty space should be filled with objects. Empty moments should be distracted away with entertainment. But perhaps there is value in emptiness itself, in the space it provides for reflection, possibility, and the emergence of new patterns and structures. The Buddhist concept of shunyata, often translated as emptiness, but carrying connotations of openness and potential, offers a particularly resonant framework for thinking about cosmic voids. In this tradition, emptiness is not mere nothingness, but rather the absence of an inherent independent existence. All things exist interdependently, defined by their relationships rather than by any essential nature. The supervoid, similarly, is defined by its relationship to the surrounding cosmic web, not as an absolute absence, but as a region where certain types of structure are minimized while others persist or even flourish. Astronomer and author Carl Sagan once observed that the cosmos is within us. We are made of star stuff. This famous quote reminds us of our deep connection to the universe, our bodies composed of elements forged in stellar furnaces billions of years ago. But we might equally observe that the void is within us too. The atoms that make up our bodies are mostly empty space, with vast distances, relatively speaking, between nucleus and electrons. Our solidity is largely illusory, a product of electromagnetic forces rather than continuous substance. This perspective is not meant to diminish human experience, but to place it within a cosmic context that enriches our understanding of ourselves. We are participants in a universe that expresses itself through both fullness and emptiness, through matter and void, through presence and absence. The supervoid, as an extreme expression of cosmic emptiness, helps us appreciate this duality and our place within it. As we contemplate the billion light-year void, we might also reflect on the limitations of human knowledge and the humility appropriate to our cosmic situation. Despite the remarkable progress of modern astronomy and cosmology, there remain profound mysteries about the nature of the universe. Dark matter and dark energy, which together make up about 95% of the cosmos, are still poorly understood. The origin of the universe's structure, from quantum fluctuations to the cosmic web, involves physics at the very edge of our theoretical understanding. The supervoid stands as a reminder of these limits of structure, so extreme that it challenges our standard cosmological model, yet so distant and diffuse that it stretches our observational capabilities. It embodies both the triumph of human intellect in detecting and characterizing such a vast cosmic structure and the ongoing challenge of fully comprehending our complex universe. This combination of achievement and limitation characterizes the scientific enterprise itself. Each discovery answers some questions, while raising others. Each advance in understanding reveals new horizons of ignorance. The supervoid exemplifies this dynamic, offering provisional answers about cosmic structure formation, while posing deeper questions about the nature of cosmic emptiness and its relationship to the universe's largest scales. There is a certain comfort in this ongoing quest, this endless dialogue between knowledge and mystery. It suggests that the universe will never become mundane or fully tamed by human understanding, that there will always be phenomena that inspire wonder and challenge our concepts. The supervoid, with its enormous scale and subtle effects, seems particularly suited to this role, offering a cosmic mystery that resists simple resolution. As we near the end of our journey through the billion light-year void, it's worth considering what this cosmic emptiness means for our future. The universe appears to be entering an era dominated by dark energy, where the expansion of space accelerates and structures become increasingly isolated. In the very far future, trillions of years hence, each galaxy or small cluster of galaxies will become an island in an otherwise empty cosmos, with all other structures having receded beyond the observable horizon. In this scenario, the entire observable universe will eventually resemble a vast void, with just a single galaxy or galaxy cluster visible to any hypothetical observers. Our descendants, should humanity or its successors survive to such epochs, would view a night sky devoid of other galaxies, with no direct evidence of the rich cosmic web that once existed. The supervoid, in this sense, offers a preview of the universe's distant future, a glimpse of the cosmic loneliness that may await intelligent life in the eons to come. Yet even in this scenario, meaning and purpose need not be diminished. The universe will continue to evolve, to express its fundamental laws and processes, to manifest beauty and complexity at various scales. Conscious beings will still be able to explore and understand their environment, to create art and science, to find significance in their existence. The void, rather than negating these possibilities, might even enhance them by providing a stable, quiet backdrop for their unfolding. This perspective brings us back to the present moment and our current relationship with the supervoid. This vast cosmic emptiness, far from being a mere curiosity or anomaly, offers a profound opportunity for reflection on the nature of the universe and our place within it. It reminds us of the enormous scales of space and time that contextualize human existence, not to diminish our significance, but to place it within a larger framework of meaning. The supervoid also reminds us of the essential role of absence in defining presence, of emptiness in giving form to fullness. Without the vast voids of the cosmic web, the filaments and clusters would not exist as distinct structures. Without the dark energy that fills these voids and drives the accelerating expansion of the universe, the cosmos would not have evolved as it has. Emptiness, far from being meaningless, is essential to the universe's nature and development. As we conclude this chapter, let us embrace the paradox of finding meaning in emptiness, of discovering richness in void. The billion light-year supervoid, with all its mysteries and challenges, its scientific significance and philosophical resonance, stands as a testament to the universe's endless capacity to surprise and inspire us. In the greatest emptiness, we find some of our deepest insights. In absence, we discover profound presence. In the final chapter, we will draw together the threads of our exploration, from the scientific discovery of the supervoid to its philosophical implications, and consider what it tells us about the ongoing human endeavor to understand the cosmos and our place within it. Having explored the discovery, properties, and theoretical implications of the supervoid, as well as the perspective it offers on our place in the cosmos, we now turn our gaze toward the future. What new observations might shed additional light on this cosmic mystery? How might upcoming telescopes and surveys deepen our understanding of the supervoid and its relationship to the cold spot in the cosmic microwave background? The history of astronomy has been marked by technological leaps that have repeatedly transformed our understanding of the universe. From Galileo's first telescopic observations of Jupiter's moons to the Hubble Space Telescope's deep views of distant galaxies, each advance in observational capability has opened new windows onto the cosmos. We now stand at the threshold of another such transformation, with a new generation of observatories poised to revolutionize our view of the universe. These future observational facilities promise to provide unprecedented insights into the supervoid and other large-scale structures in the universe. By mapping the distribution of galaxies with greater precision, measuring the properties of the cosmic microwave background with higher sensitivity, and probing the nature of dark matter and dark energy with new techniques, they may finally resolve the mystery of the supervoid or reveal even deeper puzzles in our understanding of the cosmos. One of the most ambitious upcoming projects is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, currently under construction on Cerro Pachón in Chile. Named after the pioneering astronomer who provided some of the first evidence for dark matter, the Rubin Observatory features an 8.4-meter primary mirror and the largest digital camera ever built for astronomy, with 3.2 billion pixels. Beginning regular operations in the mid-2020s, it will conduct the Legacy Survey of Space and Time, LSST, observing the entire southern sky every few nights for 10 years. The LSST will detect billions of galaxies, mapping their three-dimensional distribution with unprecedented detail and depth. By repeatedly imaging the same regions of sky, it will also measure the subtle motions and changes in galaxies over time, potentially revealing the dynamics of the cosmic web in action. For the supervoid region, this will translate into a much more comprehensive census of galaxies, allowing astronomers to map its size, shape, and internal structure with far greater precision than current surveys allow. The Rubin Observatory's combination of wide field coverage and depth makes it particularly well suited for studying cosmic voids. Current galaxy surveys often suffer from either limited sky coverage or insufficient depth, making it difficult to map the full extent of large structures like the supervoid. The LSST will provide a more complete picture, potentially revealing whether the supervoid is indeed an extraordinary structure or whether it is more comparable to other large voids in the universe. Moreover, the repeated observations of the LSST will allow astronomers to measure weak gravitational lensing effects with unprecedented precision. Weak lensing, the subtle distortion of background galaxy images by intervening matter, provides a direct probe of the distribution of both visible and dark matter. By measuring these distortions around and within the supervoid, astronomers can map its total mass content, not just the galaxies visible within it. This will provide crucial constraints on the void's density profile and its potential effects on the cosmic microwave background. Another groundbreaking observatory is the Nancy Grace Roman Space Telescope, named after the mother of Hubble, who was instrumental in the development of the Hubble Space Telescope. Scheduled for launch in the mid-2020s, the Roman telescope will feature a 2.4-meter mirror, the same size as Hubble's, but with a field of view 200 times larger, allowing it to survey the sky much more rapidly. The Roman telescope's wide-field infrared camera will be particularly valuable for studying the supervoid and its surroundings. Infrared light is less affected by dust than optical light, allowing for clearer views of distant galaxies. Additionally, as the universe expands, the light from distant galaxies is stretched to longer wavelengths, a phenomenon known as redshift. For the most distant galaxies, much of their light is shifted into the infrared, making infrared observations essential for mapping the three-dimensional structure of the cosmos at great distances. The Roman telescope will conduct several surveys designed to address fundamental questions in cosmology, including the High Latitude Wide Area Survey, which will cover thousands of square degrees of the sky and detect millions of galaxies. This survey will provide complementary data to the LSST, with different strengths and systematics, allowing for more robust constraints on the properties of the supervoid. A third major facility is the Euclid Space Telescope, launched by the European Space Agency in July of 2023. Euclid is specifically designed to investigate dark energy and dark matter by mapping the three-dimensional distribution of galaxies across 10 billion light-years. It carries two instruments, a visible light imager and a near-infrared spectrometer and photometer. Together, these instruments will allow Euclid to measure the shapes, distances, and spectral properties of billions of galaxies. Euclid's primary science goals align perfectly with the questions raised by the supervoid. By mapping the large-scale structure of the universe with unprecedented precision, it will provide a comprehensive census of cosmic voids, including detailed measurements of their sizes, shapes, and density profiles. This will place the supervoid in context, revealing whether it is truly an outlier or merely one of many similar structures in the cosmic web. Moreover, Euclid's measurements of the expansion history of the universe will provide crucial constraints on dark energy, the mysterious force driving the accelerating expansion of the cosmos. Since voids are particularly sensitive to the effects of dark energy, observations of the supervoid and other large voids could offer unique insights into its properties. If the supervoid's size or emptiness cannot be explained within the standard cosmological model, it might point to novel features of dark energy or even modifications to Einstein's theory of gravity. The James Webb Space Telescope, JWST, launched in December 2021, represents another powerful tool for studying the supervoid and its implications. With its 6.5-meter primary mirror and suite of infrared instruments, JWST can observe extremely distant galaxies with unprecedented sensitivity and resolution. While its field of view is smaller than that of survey telescopes like Rubin or Euclid, JWST can conduct detailed follow-up observations of interesting regions identified by these wider field surveys. For the supervoid, JWST could provide detailed observations of the few galaxies that do exist within this cosmic desert. By studying their properties, including their star formation rates, gas content, and chemical composition, astronomers can test theories about how galaxies evolve in such isolated environments. This would help determine whether the supervoid's emptiness is primordial, dating back to the early universe, or whether it developed more recently through the evacuation of matter from an initially more typical region. Ground-based radio telescopes will also play a crucial role in future studies of the supervoid. The Square Kilometre Array, SKA, under construction in Australia and South Africa, will be the world's largest radio telescope when completed. With a collecting area of 1 square kilometre spread across thousands of individual antennas, the SKA will be able to detect extremely faint radio signals from distant galaxies and map the distribution of neutral hydrogen gas throughout the universe. Neutral hydrogen, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. By detecting this emission from galaxies at different distances, radio astronomers can map the three-dimensional distribution of matter with a technique independent of optical surveys. This provides a complementary view of cosmic structure that is subject to different observational biases and systematic effects. For the supervoid, SKA observations could reveal whether it is truly devoid of matter or whether it contains diffuse gas that has not yet condensed into galaxies. This would provide crucial insights into the void's formation history and its relationship to the cosmic web. If the void contains significant amounts of neutral hydrogen, it would suggest that galaxy formation has been suppressed in this region, rather than matter being entirely absent. Beyond these new observatories, improvements in data analysis techniques and computational modeling will also advance our understanding of the supervoid. Machine learning algorithms, which have already begun to transform astronomical data analysis, will become increasingly powerful tools for identifying patterns and anomalies in the vast datasets produced by next-generation telescopes. For example, convolutional neural networks, a type of deep learning algorithm particularly adept at image recognition, can be trained to identify voids and other structures in galaxy surveys with greater accuracy and consistency than traditional methods. These algorithms can detect subtle patterns that might be missed by human analysts or simpler computational approaches, potentially revealing new insights about the supervoid's structure and properties. Similarly, advances in cosmological simulations will allow for more sophisticated modeling of void formation and evolution. Current simulations can already reproduce many features of the cosmic web, including voids of various sizes, but they typically struggle to produce structures as extreme as the supervoid appears to be. By increasing the volume and resolution of these simulations, and by exploring a wider range of cosmological parameters, researchers may be able to determine whether the supervoid can be accommodated within the standard cosmological model, or whether it points to new physics. These simulations will also help interpret the observational data from next-generation telescopes, allowing astronomers to test various hypotheses about the supervoid's origin and nature. By creating synthetic observations that mimic what future telescopes would see under different scenarios, researchers can develop and refine methodologies for extracting the maximum information from real observations when they become available. In addition to these broad surveys and technological advances, targeted observations of specific aspects of the supervoid may provide crucial insights. For instance, detailed measurements of the integrated Sachs-Wolf effect in the supervoid region could help clarify its relationship to the cold spot in the cosmic microwave background. This effect, whereby light from the CMB changes frequency as it passes through evolving gravitational potentials, is expected to create a temperature decrement when the light passes through a void. By correlating maps of galaxy distribution with CMB temperature maps at higher precision than currently possible, astronomers may be able to determine whether the observed cold spot can be fully explained by the ISW effect from the supervoid, or whether additional factors must be invoked. This would help resolve one of the central mysteries in the supervoid story. Is it causally connected to the cold spot, or is their alignment merely a cosmic coincidence? Another targeted approach would involve studying the few galaxies that do exist within the supervoid in greater detail. By obtaining spectroscopic measurements of these galaxies, astronomers can determine their precise distances, velocities, and physical properties. This would provide insights into the void's three-dimensional structure and the environmental effects on galaxy evolution within such extreme underdense regions. The peculiar velocities of galaxies, their motions relative to the overall expansion of the universe, are particularly informative. In and around voids, galaxies are expected to show distinctive flow patterns, moving away from the void center and towards surrounding denser regions. Precise measurements of these motions could reveal the gravitational dynamics of the supervoid and test predictions of various cosmological models, including potential modifications to gravity. The cosmic microwave background itself will continue to be a crucial source of information about the supervoid and the early universe. While the Planck satellite, which operated from 2009 to 2013, provided the most detailed all-sky map of the CMB to date, future missions promise even greater precision. Proposed CMB missions, such as CMB-S4, CMB Stage 4, a ground-based experiment planned for the late 2020s, will observe the microwave sky with unprecedented sensitivity and angular resolution. These observations will provide more detailed measurements of the cold spot and other features in the CMB, potentially revealing subtle features that current data cannot resolve. Of particular interest are the polarization properties of the CMB, the preferred orientation of the electric field in the microwave radiation. Polarization provides complementary information to temperature measurements and is less affected by foreground contamination. Detailed observations of CMB polarization in the cold spot region might reveal patterns characteristic of specific physical mechanisms, such as the integrated Sachs-Wolfe effect, or more exotic phenomena like cosmic textures or bubble collisions. Looking even further ahead, gravitational wave observations may eventually provide a completely new window on cosmic structures like the supervoid. Gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity and directly detected for the first time in 2015, propagate through the universe largely unaffected by the matter they encounter. However, they are subtly influenced by the gravitational potentials of large-scale structures, including voids. Future gravitational wave observatories, both in space and on Earth, might be able to detect the subtle distortions imprinted on gravitational waves as they traverse the supervoid. These distortions could provide a completely independent probe of the void's gravitational properties, complementing electromagnetic observations across the spectrum. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned for launch in the 2030s, will be particularly well suited for detecting low-frequency gravitational waves that might carry imprints of large-scale structure. By correlating gravitational wave observations with maps of the cosmic web derived from galaxy surveys, astronomers might identify the signatures of major voids and other structures, potentially including the supervoid. As we peer into this future of astronomical discovery, it is worth reflecting on the iterative nature of scientific progress. Each new observation builds upon previous knowledge, either reinforcing existing theories or pointing toward new directions. The supervoid and cold spot, as cosmic anomalies that challenge our understanding, play a crucial role in this process, driving us to develop more sophisticated theories and more powerful observational tools. Whether future observations confirm the supervoid as an extraordinarily rare structure that stretches the limits of the standard cosmological model, or reveal it to be a more ordinary feature that appeared exceptional due to the limitations of our current data, the journey of discovery will have advanced our understanding of the cosmos. Each possibility teaches us something valuable about the universe and about the process of scientific inquiry itself. If the supervoid is confirmed as a truly extraordinary structure, it may point to new physics beyond the standard model, such as novel properties of dark energy, modifications to gravity on the largest scales, or primordial features imprinted during the earliest moments of the universe. Such a discovery would open new frontiers in theoretical physics and cosmology, potentially revolutionizing our understanding of the fundamental nature of reality. On the other hand, if improved observations reveal the supervoid to be less extreme than it currently appears, this would reinforce the remarkable success of the Lambda CDM model, which has already explained a wide range of cosmic phenomena with remarkable precision. It would demonstrate the power of this model to accommodate apparent anomalies once they are more fully understood, a testament to its robustness and flexibility. Either outcome would represent a triumph for the scientific method, with its emphasis on empirical observation, theoretical interpretation, and the constant refinement of both through an ongoing dialogue between data and explanation. The story of the supervoid, still unfolding, exemplifies this process in action, as each new observation brings us closer to understanding this cosmic enigma. As we anticipate the flood of new data from next-generation observatories, we can be certain that our picture of the supervoid and its relationship to the cold spot will continue to evolve. New details will emerge, new patterns will be recognized, and new questions will arise. The cosmic mystery that has captivated astronomers for nearly 2 decades may be resolved, only to give way to deeper mysteries about the nature of the universe. In this ongoing quest for understanding, the billion light-year void stands as a reminder of the vast scales and complex structures that characterize our cosmos. It challenges us to expand our theoretical frameworks, to develop more powerful observational tools, and to maintain a sense of wonder at the grandeur and mystery of the universe we inhabit. In the final chapter, we will reflect on the philosophical and poetic dimensions of the supervoid, considering what this vast emptiness in the cosmic tapestry might tell us about meaning and purpose in a universe of such extraordinary scale and diversity. Having explored the properties of the supervoid and how voids affect the universe around them, we now turn to a more speculative question. What would it be like if our planet existed within the supervoid rather than in its actual location in the cosmos? How would the night sky appear to astronomers on such a world, and how might their understanding of the universe differ from our own? This thought experiment is not merely an exercise in imagination, but a way to understand how our particular cosmic vantage point shapes our perception of the universe. Throughout history, advances in astronomy have repeatedly shown that our place in the cosmos is less special than we once believed. The Earth is not the center of the solar system, the Sun is just one of billions of stars in the Milky Way, and our galaxy is but one among trillions in the observable universe. But what if our cosmic address were even more unremarkable, situated in the vast emptiness of the supervoid? Let us imagine a planet similar to Earth, orbiting a star like our Sun, but located deep within the supervoid, hundreds of millions of light-years from any major galaxy cluster or filament. The immediate environment of this hypothetical planet might not seem so different from our own. The planet would still orbit its star, which would provide warmth and light during the day. The star would likely be part of a small galaxy, perhaps a dwarf spiral or irregular galaxy, as these types of galaxies are more common in void regions than massive ellipticals or grand spirals. The first and most striking difference would be apparent when night falls on this void planet. The night sky would be dramatically darker and emptier than the one we see from Earth. In our sky, the Milky Way stretches as a bright band of light, containing so many stars that they blend together into a continuous glow. An observer on a clear, dark night can see thousands of individual stars with the naked eye, most of which are relatively nearby neighbors within our galaxy. But on a planet within the supervoid, the home galaxy would likely be much smaller than the Milky Way, containing perhaps a few billion stars, rather than hundreds of billions. If the planet were located in a position similar to Earth's, near the outskirts of this small galaxy, the galactic center might appear as a dim, diffuse patch of light, rather than the brilliant core visible in our night sky. The band of the galaxy across the sky would be fainter, narrower, and less structured, with fewer bright star-forming regions and dust lanes. The relative isolation of a void galaxy would mean fewer nearby giant molecular clouds, the dense regions of gas and dust where new stars are born. This would result in less active star formation and fewer bright blue stars, which have short lifespans and thus serve as indicators of recent star formation. The stellar population in the visible night sky would be dominated by older, redder stars, giving the band of the galaxy a more subdued, reddish hue compared to the vibrant mix of colors visible in our Milky Way. The void galaxy would also likely contain less interstellar dust, the microscopic particles that scatter and absorb starlight. In our night sky, dust obscures parts of the Milky Way, creating the distinctive dark lanes visible in the galactic band. With less dust, the void galaxy would appear more transparent, with fewer dark regions, though also less dramatic, in contrast due to the lower overall stellar density. The three-dimensional structure of the home galaxy might also differ from the Milky Way. Void galaxies tend to have more diffuse spiral arms, and less pronounced central bulges. For observers on the void planet, this would mean that the galaxy's spiral structure might be harder to discern, appearing more as subtle brightness variations than the clear spiral patterns visible in larger galaxies. The central bulge might appear as a mild brightening toward the galactic center, rather than the dramatically luminous core we observe from Earth. Beyond the home galaxy, the difference would be even more dramatic. In our sky, several neighboring galaxies are visible to the naked eye, including the Andromeda Galaxy, the Large and Small Magellanic Clouds, and the Triangulum Galaxy. With a small telescope, thousands more become visible. But from a planet in the supervoid, the nearest large galaxies might be tens or hundreds of millions of light-years away, too distant to be seen without powerful telescopes. Instead of a sky filled with the light of neighboring galaxies, observers on the void planet would see a vast darkness, broken only by the faint, fuzzy patches of a few distant galaxies at the edges of the void. These galaxies would be so far away that they would appear as they were millions or even billions of years in the past, when the universe was younger and galaxies were still forming. This visual separation from the broader cosmic web would profoundly influence the development of astronomy and cosmology on the void planet. The concept of extragalactic space, the idea that there exists a universe beyond the confines of the home galaxy, might emerge much later in the history of their science. Without clearly visible neighboring galaxies to inspire curiosity and speculation, void astronomers might initially assume that their galaxy constitutes the entirety of the universe. In our own history, the nature of spiral nebulae as distant galaxies separate from the Milky Way was a subject of intense debate in the early 20th century, culminating in the Great Debate between Harlow Shapley and Heber Curtis in 1920. This controversy was resolved when Edwin Hubble measured the distance to Andromeda using Cepheid variable stars, proving conclusively that it lay far beyond the boundaries of our galaxy. But for void astronomers, without nearby galaxies to observe, this crucial step in understanding the scale of the universe might be significantly delayed. The challenge of measuring vast cosmic distances would be particularly daunting for void astronomers. In our history, the cosmic distance ladder, the series of methods astronomers use to measure increasingly large distances, was built step by step, with each rung allowing us to calibrate the next. Parallax measurements of nearby stars enabled the calibration of intrinsic brightness for certain types of variable stars, which in turn allowed measurements to nearby galaxies, and so on. For void astronomers, the enormous gap between their home galaxy and the nearest large galaxies would create a missing rung in this ladder, making it difficult to establish the true scale of the universe. This sparse cosmic landscape would have profound implications for the development of astronomy and cosmology on such a world. The absence of nearby galaxies would make it much more difficult for astronomers to discover the true nature and scale of the universe. The concept of galaxies as island universes, collections of stars separated by vast distances, might take much longer to establish without clear examples visible in the night sky. When void astronomers did eventually discover distant galaxies with their telescopes, they would face additional challenges in understanding their nature. The galaxies visible from the void planet would be predominantly those at the edges of the void, which might have different properties from the general galaxy population. These edge galaxies often experience unique environmental effects from their position at the interface between the void and the filaments of the cosmic web. They tend to be more actively forming stars and may have distorted shapes due to gravitational interactions with the surrounding structure. Void astronomers might initially think these properties were typical of all galaxies, potentially leading to skewed theories about galactic evolution. The discovery of the expanding universe might also be delayed. In our world, this discovery came from observations showing that most galaxies are moving away from us, with more distant galaxies receding faster. This pattern, now known as Hubble's law, provided the first evidence for the Big Bang theory. But with fewer and more distant galaxies to observe, void astronomers might struggle to discern this pattern until they developed much more advanced technology. The measurement of galactic redshifts, the stretching of light from distant galaxies due to cosmic expansion, would be particularly challenging for void astronomers. The nearest galaxies visible from the void planet would already be so distant that their redshifts would be substantial. Without nearby galaxies with smaller redshifts to establish the linear relationship between distance and recession velocity, Void astronomers might initially interpret these redshifts as indicating unusually high velocities rather than cosmic expansion. Furthermore, the galaxies visible from the void would predominantly lie in particular directions toward the filaments and walls surrounding the void, rather than being distributed uniformly across the sky. This anisotropic distribution might make it harder for void astronomers to recognize the isotropic nature of cosmic expansion, potentially leading to theories of a preferred direction or center to the universe. Another crucial development in our understanding of the cosmos was the discovery of the cosmic microwave background radiation, CMB, in 1964. This faint radiation, coming uniformly from all directions in the sky, provided strong evidence for the Big Bang theory and has since become one of our most important tools for studying the early universe. Void astronomers would still be able to detect the CMB, as it permeates all of space, but their interpretation of it might differ in subtle ways. Ironically, once void astronomers did develop sufficient technology to map the large-scale structure of the universe, they might actually have an advantage in certain types of observations. The relative emptiness of a void region means less contamination from foreground sources, potentially allowing for clearer observations of the cosmic microwave background radiation and distant galaxies at the edge of the observable universe. The cosmic microwave background, that faint glow left over from the Big Bang, would still permeate the void just as it does the rest of the universe. But without the intervening matter found in denser regions, the CMB might appear more uniform to void observers, with fewer secondary anisotropies caused by the integrated Sachs-Wolf effect and other interactions with large-scale structure. In our location within the cosmic web, the CMB we observe is slightly affected by the matter along our line of sight. As CMB photons travel through space, they gain energy when falling into gravitational wells of galaxy clusters and lose energy when climbing out. Since the universe is expanding, these wells become shallower over time, resulting in a net energy loss for the photons and creating subtle temperature variations in the CMB. This integrated Sachs-Wolf effect is most pronounced in regions with large-scale structures like supervoids and superclusters. Observers within the supervoid would see a CMB with less of this effect along most lines of sight, as there would be fewer large-scale structures between them and the surface of last scattering, the region from which the CMB originates. The CMB would appear more pristine, closer to its original state when it was first emitted 380,000 years after the Big Bang. This more pristine view of the CMB might allow void astronomers to measure certain cosmological parameters with greater precision. The tiny temperature fluctuations in the CMB, which reflect the density variations in the early universe that seeded cosmic structure, would be more clearly visible without the additional fluctuations induced by intervening matter. This could potentially give void astronomers an advantage in studying the earliest moments of the universe, including the period of cosmic inflation thought to have occurred in the first fraction of a second after the Big Bang. However, they would face the opposite challenge from us when trying to understand the cold spot. While we observe a cold region aligned with a void and must determine whether this is causal or coincidental, void astronomers would observe a cold region without an apparent void along the line of sight. They might be led to consider more exotic explanations, such as cosmic textures or bubble collisions, without the supervoid as a potential contributing factor. Studying the cold spot from within the supervoid would present a fascinating perspective shift. From our vantage point, we see a cold spot in the CMB aligned with a void along our line of sight, and we debate whether the void causes the cold spot through the integrated Sachs-Wolf effect. From within the void, astronomers would see the same cold spot, but would not detect a void in that direction, as they would already be inside it. They might search in vain for a structure along that line of sight to explain the temperature decrement, potentially leading them to consider more exotic explanations or to question the fundamental assumptions of their cosmological models. This scenario highlights the importance of understanding our observational biases and the limitations imposed by our particular cosmic vantage point. Whether we observe from within a void or from a more typical region of the cosmic web, our perspective inevitably shapes our interpretation of the cosmos. The scientific journey involves not just collecting observations, but recognizing and accounting for these biases to arrive at a more objective understanding of the universe. The development of cosmological theories might follow a different path on a void planet. The discovery that they lived in an unusually underdense region of the universe would likely come as a surprise, overturning the assumption that their vantage point was typical. This realization might lead to earlier consideration of alternatives to the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. In our cosmological history, the cosmological principle was adopted partly for philosophical reasons, the idea that there should be no special or privileged locations in the universe, and partly for mathematical simplicity, as it greatly simplifies the equations of general relativity when applied to the universe as a whole. Void astronomers, upon discovering their unusual location, might be more reluctant to embrace this principle, perhaps developing more complex models that explicitly account for large-scale inhomogeneities. Void astronomers might be more inclined to develop models where the universe has a hierarchical structure, with voids nested within larger voids, and their location near the center of a particularly large void being just a cosmic coincidence. These models would need to be reconciled with other observations, such as the remarkable uniformity of the cosmic microwave background, leading perhaps to more complex early theories about the universe's origin and evolution. One intriguing possibility is that void astronomers might develop something akin to the void model, proposed by some cosmologists as an alternative to dark energy. In this model, we live near the center of a giant void, and the apparent acceleration of the universe's expansion is not due to dark energy, but is instead an illusion created by our position within this underdense region. While this model has been largely rejected based on our observations, void astronomers might find it more plausible given their cosmic location, potentially delaying their discovery of the true nature of dark energy. The perception of cosmic time might also differ for void astronomers. In our location within a typical density region of the universe, we experience the cosmic expansion at approximately the average rate. But within a void, the expansion proceeds somewhat faster due to the lower density of matter. This difference, while subtle, accumulates over billions of years and affects how the history of the universe would be measured and understood. For example, void astronomers might measure a higher value of the Hubble constant, the parameter that describes the current expansion rate of the universe. This could lead them to calculate a younger age for the universe than we do, at least until they recognize their location within a void and accounted for its effects on their measurements. The void environment would also affect the formation and evolution of the planetary system itself. Star and planet formation requires dense clouds of gas and dust, which are less common in void regions. The stars that do form in voids tend to be somewhat less enriched with heavy elements, which are produced in supernovae and spread through the interstellar medium by stellar winds and explosions. With fewer nearby stars and less stellar recycling of materials, a planetary system in a void might have a slightly different composition, perhaps with relatively less carbon, oxygen, silicon, and other elements essential for terrestrial planets and life as we know it. The chemical evolution of galaxies is a complex process that depends on multiple generations of stars. The first stars, formed from the primordial hydrogen and helium produced in the Big Bang, forged heavier elements in their cores and dispersed them when they exploded as supernovae. Subsequent generations of stars incorporated these heavier elements, creating even more complex atoms in their nuclear furnaces. This process, repeated over billions of years, gradually enriched the interstellar medium with the elements necessary for planets and life. In void regions, this chemical enrichment process might proceed more slowly due to the lower density of stars and the reduced rate of stellar interactions and mergers. The interstellar medium would contain a lower abundance of heavy elements, a property astronomers call metallicity. Stars forming in this environment would incorporate less of these elements, potentially affecting the types of planetary systems they could form. Research on exoplanets in our region of the galaxy has suggested a correlation between stellar metallicity and the prevalence of giant planets. Stars with higher metallicity are more likely to host Jupiter-sized planets, perhaps because the additional heavy elements provide more building material for planet formation. If this trend holds in void regions, planetary systems might have fewer giant planets, potentially resulting in different dynamical histories and more stable conditions for any terrestrial planets. The reduced metallicity might also affect the size and composition of terrestrial planets themselves. Planets forming around low metallicity stars might be smaller on average and have different internal structures. The core of Earth, composed primarily of iron and nickel, makes up about a third of our planet's mass and generates the magnetic field that helps shield the surface from harmful radiation. A planet with less available iron might have a smaller core and a weaker magnetic field, potentially affecting its habitability. However, once a suitable planet did form, the conditions for life might not be so different. The local star would provide the same types of energy, and the basic physics and chemistry governing the development of life would be the same. The isolation of the planetary system might even provide some advantages, with fewer nearby supernovae or gamma-ray bursts to threaten developing life with extinction-level radiation events. The evolution of life on a void planet might proceed along pathways not so different from those on Earth. The fundamental building blocks of life, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, would still be present, albeit perhaps in different relative abundances. The basic mechanisms of evolution through natural selection would operate according to the same principles. The primary energy source for most life would still likely be the parent star, with photosynthesis or something analogous serving as the foundation of the food web. Where the void environment might most significantly impact the development of life is in the reduced frequency of extinction events. On Earth, astronomers have suggested that some mass extinctions might have been triggered by cosmic events, such as nearby supernovae, gamma-ray bursts, or even periodic passages through denser regions of the galactic disk. A planetary system in an isolated void galaxy would be subject to fewer such external threats, potentially allowing for more continuous and stable evolutionary development. This relative cosmic isolation might have interesting implications for the types of intelligence and civilization that could develop on a void planet. On Earth, our understanding of the universe has been profoundly shaped by what we can observe. From the patterns of stars that inspired early mythology to the galaxies and cosmic microwave background that inform our modern cosmology, a civilization developing under the darker, emptier skies of a void world might form very different concepts about their place in the cosmos. The question of life's prevalence and distribution would take on a different character for void astronomers. In our position within a galaxy-rich region of the cosmos, we can observe many nearby planetary systems and search for signs of life. Projects like SETI, the search for extraterrestrial intelligence, scan the stars of our galaxy for artificial signals. But for void astronomers, the nearest potentially habitable planets beyond their own solar system might be much farther away, making such searches far more challenging. The vast distances between stars in a void galaxy might make interstellar communication or travel seem even more daunting than it does to us. While we contemplate sending probes to nearby stars like Proxima Centauri, just over 4 light-years away, the nearest stellar neighbor to a void planet might be tens or hundreds of light-years distant. This extreme isolation might influence how a void civilization conceptualizes space exploration and their potential place in a broader galactic community. If void astronomers did develop radio astronomy and begin searching for extraterrestrial signals, they would face additional challenges. The greater average distance between stars would mean that any signals would be fainter by the time they reach the void planet. The reduced number of targets would lower the probability of detecting a signal. And without a rich galactic neighborhood to inspire speculation about alien civilizations, the void culture might be less inclined to invest resources in such searches in the first place. This cosmic isolation might also shape the void civilization's perspective on their place in the universe. While we have gradually discovered our non-central position in ever larger cosmic structures, void astronomers would eventually discover that they occupy an unusually empty region. This might lead to a different kind of cosmic humility, a recognition not that they are ordinary, but that they are extraordinarily isolated, inhabitants of a cosmic desert stretching for hundreds of millions of light-years in all directions. The psychological and cultural impact of this discovery could be profound. Throughout human history, our understanding of the cosmos has shaped our philosophies, religions, and worldviews. The Copernican revolution, which displaced Earth from the center of the universe, has been cited as a catalyst for the scientific revolution and the Enlightenment, fundamentally altering how we see our place in nature. For a void civilization, the discovery of their extreme isolation might similarly transform their self-perception and cultural development. Would void dwellers feel special upon learning of their unusual cosmic address? or would they feel abandoned in a cosmic desert? Would their isolation inspire a greater appreciation for the rarity and value of life, or would it foster a sense of cosmic insignificance? These questions, while speculative, highlight how our physical location in the universe can shape our metaphysical understanding of existence. The practical implications of this isolation would become apparent if the Void civilization ever developed the technology and ambition for interstellar travel. The distances to neighboring star systems would likely be greater than those in our region of the Milky Way, making even the closest interstellar journeys more challenging. And if they ever aspired to intergalactic travel, they would face even greater obstacles, with the nearest large galaxies lying at nearly unimaginable distances. Launching an interstellar probe similar to our Voyager spacecraft would require substantially more patience for Void astronomers. While our Voyager probes will pass relatively close to several stars in the next few tens of thousands of years, a Void probe might travel for millions of years before encountering another star system. This vast timescale might necessitate different approaches to interstellar exploration, perhaps emphasizing extremely long-lived, self-replicating probes that could sustain their mission across cosmological timescales. Similarly, any attempts at interstellar communication would face greater challenges. Radio signals, traveling at the speed of light, would take decades or centuries to reach even the nearest stars. Any conversation across these distances would span multiple generations, requiring institutional memory and commitment beyond anything in our experience. The Void civilization might need to develop unique approaches to such long-term projects, perhaps creating special social structures or artificial intelligence systems dedicated to maintaining these multi-generational efforts. As the Void civilization's astronomical knowledge advanced, they would eventually map the large-scale structure of the universe and recognize the cosmic web of filaments, walls, and clusters surrounding their void. They might come to see themselves as inhabitants of a cosmic bubble, with denser regions of the universe forming a distant shell around them. This perspective might inspire different metaphors and analogies for understanding their place in the cosmos, perhaps seeing the void as a kind of cosmic clearing or oasis, rather than the cosmic desert we might perceive it to be. The mapping of the cosmic web would be a monumental achievement for Void astronomers, requiring observations of extremely distant galaxies across vast regions of space. They would eventually recognize that the galaxies are not distributed randomly, but form a network of filaments, walls, and clusters, with voids like their own filling the spaces in between. This realization would fundamentally transform their understanding of cosmic structure, much as the discovery of the cosmic web has transformed our own. From their position deep within a void, they would observe the surrounding filaments and walls as a distant, roughly spherical shell of galaxies. This shell would not be uniform, but would show variations in density and structure, with some regions containing denser clusters and others showing more diffuse filaments. The visualization of this three-dimensional structure would require sophisticated observational techniques and data analysis, potentially driving the development of new astronomical methods and technologies. The recognition of their position within this cosmic web might inspire new cosmological theories and models. Void astronomers might develop specialized mathematical tools for describing the evolution of underdense regions, or create simulations focused on understanding how such extreme voids form and grow. Their unique perspective might lead to insights about void dynamics that would be less obvious to astronomers in denser regions, potentially advancing our understanding of these important cosmic structures. If the Void civilization continued to advance, eventually developing space telescopes and other technology comparable to our own, they would ultimately arrive at a similar understanding of the universe's history and structure. The same physical laws govern the cosmos regardless of the observer's location, and the same evidence for the Big Bang, cosmic inflation, dark matter, and dark energy would eventually be discovered, albeit perhaps in a different sequence and with different initial interpretations. Advanced Void astronomers would recognize the cosmic microwave background as the remnant radiation from the early universe, just as we do. They would observe the abundance of light elements like hydrogen, helium, and lithium, matching the predictions of Big Bang nucleosynthesis. They would detect the accelerating expansion of the universe through observations of distant supernovae, and they would measure the clustering of galaxies and the pattern of temperature fluctuations in the CMB, revealing the underlying cosmological parameters. Through these observations, they would construct a model of the universe's history, from its origin in the Big Bang through the formation of structure and the emergence of galaxies, stars, and planets. This model would match our own in its essential features, differing perhaps in emphasis or in the confidence assigned to certain aspects, but ultimately describing the same cosmic history and future. In this way, our thought experiment reveals both the contingency and the universality of cosmic knowledge. The path to understanding the universe depends on our particular vantage point, on what we can see and measure from our corner of the cosmos. But the destinazione, comprehensive understanding of the physical universe, is ultimately the same regardless of where we begin the journey. The supervoid, that vast cosmic emptiness that challenges our theories and stretches our understanding of the cosmos, serves as a reminder of the extraordinary diversity of environments within our universe. From the dense cores of galaxy clusters to the emptiest voids, from planets circling solitary stars to those in rich stellar neighborhoods, the cosmos offers a multitude of perspectives from which conscious beings might contemplate their existence. As we gaze into the cold spot and the supervoid aligned with it, we are looking not just at an astronomical anomaly, but at an alternate cosmic context, a different kind of place within the same vast universe that we all inhabit. By imagining how the universe would appear from within this void, we gain a deeper appreciation for how our own cosmic address shapes our understanding of the cosmos. In the next chapter, we will look to the future, exploring how upcoming telescopes and surveys might shed new light on the supervoid mystery and what these observations might tell us about the fundamental nature of our universe. D. Our non-central position in ever larger cosmic structures, void astronomers would eventually discover that they occupy an unusually empty region. This might lead to a different kind of cosmic humility, a recognition not that they are ordinary, but that they are extraordinarily isolated, inhabitants of a cosmic desert stretching for hundreds of millions of light years in all directions. The practical implications of this isolation would become apparent if the void civilization ever developed the technology and ambition for interstellar travel. The distances to neighboring star systems would likely be greater than those in our region of the Milky Way, making even the closest interstellar journeys more challenging. And if they ever aspired to intergalactic travel, they would face even greater obstacles, with the nearest large galaxies lying at nearly unimaginable distances. As the void civilization's astronomical knowledge advanced, they would eventually map the large-scale structure of the universe and recognize the cosmic web of filaments, walls, and clusters surrounding their void. They might come to see themselves as inhabitants of a cosmic bubble, with denser regions of the universe forming a distant shell around them. This perspective might inspire different metaphors and analogies for understanding their place in the cosmos, perhaps seeing the void as a kind of cosmic clearing or oasis, rather than the cosmic desert we might perceive it to be. If the void civilization continued to advance, eventually developing space telescopes and other technology comparable to our own, they would ultimately arrive at a similar understanding of the universe's history and structure. The same physical laws govern the cosmos regardless of the observer's location, and the same evidence for the Big Bang, cosmic inflation, dark matter, and dark energy would eventually be discovered, albeit perhaps in a different sequence and with different initial interpretations. In this way, our thought experiment reveals both the contingency and the universality of cosmic knowledge. The path to understanding the universe depends on our particular vantage point, on what we can see and measure from our corner of the cosmos. But the destinazione, comprehensive understanding of the physical universe, is ultimately the same regardless of where we begin the journey. The supervoid, that vast cosmic emptiness that challenges our theories and stretches our understanding of the cosmos, serves as a reminder of the extraordinary diversity of environments within our universe. From the dense cores of galaxy clusters to the emptiest voids, from planets circling solitary stars to those in rich, stellar neighborhoods, the cosmos offers a multitude of perspectives from which conscious beings might contemplate their existence. As we gaze into the cold spot and the supervoid aligned with it, we are looking not just at an astronomical anomaly, but at an alternate cosmic context, a different kind of place within the same vast universe that we all inhabit. By imagining how the universe would appear from within this void, we gain a deeper appreciation for how our own cosmic address shapes our understanding of the cosmos. In the next chapter, we will look to the future, exploring how upcoming telescopes and surveys might shed new light on the supervoid mystery and what these observations might tell us about the fundamental nature of our universe. Having explored the discovery, mapping, and theoretical significance of the supervoid, we now turn to a broader question: how do cosmic voids, including extraordinary structures like the supervoid, affect the universe around them? Far from being mere absences in the cosmic tapestry, voids are dynamic participants in cosmic evolution, influencing everything from the properties of nearby galaxies to the overall expansion of the universe. Cosmic voids might initially seem like passive features, empty regions left behind as matter flows toward denser structures. But in reality, voids are active components of the cosmic web, regions where the fundamental forces of nature operate in distinctive ways. Their effects extend far beyond their boundaries, rippling through the cosmos and leaving imprints that astronomers can detect and measure. One of the most direct effects of voids is on the galaxies that reside within and around them. Galaxies that form and evolve within void regions experience very different conditions than those in denser environments like clusters and filaments. These void galaxies provide a unique laboratory for studying how environment shapes galactic evolution. Unlike galaxies in clusters, void galaxies grow in relative isolation, rarely interacting or merging with other galaxies. They tend to be smaller, bluer, and more gas-rich than their counterparts in denser regions. The blue color indicates ongoing star formation, suggesting that void galaxies continue to form new stars at a relatively steady rate, rather than experiencing the sudden bursts of star formation triggered by galaxy mergers and interactions. Studies of void galaxies have revealed that they typically have more diffuse stellar halos, less pronounced bulges, and more extended disks than galaxies of similar mass in denser environments. Their rotation curves, which show how the rotational velocity varies with distance from the center, often rise more gradually, indicating a more uniform distribution of mass. These properties suggest that void galaxies evolve through secular processes, gradual changes driven by internal dynamics rather than external influences. The gas content of void galaxies is another distinguishing feature. They tend to have higher fractions of neutral hydrogen, the fuel for star formation, relative to their stellar mass. This abundant gas reservoir allows them to sustain star formation over longer periods. However, the star formation efficiency, the rate at which gas is converted into stars, is typically lower in void galaxies, perhaps due to the absence of external compression mechanisms that can trigger star formation in denser environments. The morphology, or shape, of void galaxies also reflects their isolated environment. They are more commonly disk-dominated, with a higher fraction of spiral and irregular galaxies compared to the mix found in denser regions. Elliptical galaxies, which are thought to form primarily through mergers, are relatively rare in voids. This morphological distribution provides further evidence that void galaxies evolve with minimal influence from surrounding galaxies. The study of void galaxies has been advanced by dedicated observational programs like the Void Galaxy Survey, which has systematically observed galaxies in nearby voids using radio, optical, and ultraviolet telescopes. By comparing the properties of these galaxies to those in average and dense environments, astronomers can isolate the effects of environment on galaxy evolution. While individual void galaxies evolve differently from those in denser regions, the collective distribution of galaxies around voids also shows distinctive patterns. Observations and simulations have revealed that galaxies are not distributed randomly within voids, but tend to form tenuous filaments and sheets that thread through the emptiness. These void substructures are similar to the more prominent filaments and walls of the cosmic web, but on a smaller scale and with lower density. The arrangement of galaxies around void boundaries is particularly interesting. Voids are often surrounded by a shell of galaxies with specific properties and dynamics. These galaxies are typically more massive and redder than those within the void, but less massive and bluer than those in dense clusters. They form what astronomers call void walls, the transitional regions between the emptiness of voids and the denser filaments and clusters beyond. The galaxies in void walls are subject to unique environmental effects. They experience gravitational influences from both the void and the surrounding structures, creating distinctive patterns of motion. Studies have shown that these galaxies tend to flow away from the void center, contributing to the void's expansion, while also being pulled toward nearby filaments and clusters. This complex dynamics shapes their evolution and properties in ways that are still being investigated. Beyond their effects on individual galaxies, voids influence the large-scale dynamics of the cosmic web. One of the most significant effects is on the expansion of space itself. According to Einstein's theory of general relativity, the expansion rate of the universe is affected by the distribution of matter and energy. Regions with less matter, such as voids, expand faster than regions with more matter, such as clusters and filaments. This differential expansion creates what cosmologists call the void phenomenon, where voids grow larger over time, not just because matter flows out of them, but because the space within them expands more rapidly than the space in denser regions. This effect becomes more pronounced in a universe dominated by dark energy, like our own, where the overall expansion of the universe is accelerating. The faster expansion within voids has several observable consequences. It creates a distinctive pattern of galaxy velocities around voids, with galaxies on the near side of a void appearing to move away from us slightly faster than expected, and galaxies on the far side appearing to move away slightly slower. This pattern, known as the void outflow, has been detected in several large voids and provides a test of both general relativity and our understanding of dark energy. The differential expansion also affects the shape of voids over cosmic time. As voids expand faster than their surroundings, they tend to become more spherical, even if they began with irregular shapes. This rounding of voids is predicted by theoretical models and has been observed in simulations of cosmic structure formation. The degree to which voids become spherical depends on the properties of dark energy and gravity, making void shapes a potential probe of fundamental physics. Another important effect of voids is their influence on the propagation of light across the cosmos. As photons from distant sources travel through the universe, they pass through regions of varying density, including voids and clusters. The gravitational effects of these structures can alter the photons' paths and energies, leaving detectable imprints on the light we observe. One such effect is gravitational lensing, where the bending of light by massive objects creates distortions and multiple images of background sources. While clusters of galaxies are the most dramatic lenses, voids can also produce lensing effects, albeit more subtle ones. Void lensing typically manifests as a slight demagnification of sources seen through a void, as the underdensity acts like a diverging lens, spreading light rays apart rather than focusing them. By measuring the statistical properties of void lensing across many voids, astronomers can probe the distribution of matter within and around voids, testing our understanding of how dark matter and visible matter are related. Recent studies using data from large surveys like the Dark Energy Survey, DES, have detected void lensing signals, providing new constraints on cosmological models. The effect of voids on light also includes the integrated Sachs-Wolfe (ISW) effect, which we explored in earlier chapters. As photons from the cosmic microwave background pass through voids, they lose energy climbing out of the gravitational well, becoming slightly cooler. This effect is enhanced in a universe with accelerating expansion, making it a valuable probe of dark energy. The ISW effect from individual voids is typically too small to detect, but by stacking the signals from many voids, astronomers have been able to measure a statistical ISW effect. These measurements provide independent evidence for the existence of dark energy and can potentially constrain its properties. The unusually large size of the supervoid makes it one of the few voids that might produce an individually detectable ISW signal, though as we've seen, the observed cold spot seems too extreme to be fully explained by this effect. Voids also influence the formation and evolution of larger structures in the universe. As voids expand, they push matter toward their boundaries, contributing to the formation and growth of filaments and walls. This process, sometimes called void collapse, is the inverse of gravitational collapse, where matter falls inward to form dense structures. In void collapse, matter is swept outward by the void's expansion, concentrating along its boundaries. The interplay between voids and the surrounding cosmic web creates a hierarchical pattern of structure, with smaller voids nesting within larger ones and filaments of varying thickness weaving between them. This hierarchy extends across an enormous range of scales, from voids a few tens of millions of light-years across to supervoids spanning billions of light-years. The relationship between voids and their surrounding structures can be understood through the watershed analogy. If we imagine the cosmic density field as a landscape, with overdense regions as mountains and underdense regions as valleys, then voids are the basins that would fill with water if this landscape were flooded. The boundaries between voids are the ridgelines that separate these basins, corresponding to the filaments and walls of the cosmic web. This watershed model has been formalized in void-finding algorithms and provides a useful framework for understanding the topological properties of the cosmic web. It explains why voids tend to be more spherical than other cosmic structures, why they have a characteristic size distribution, and why they often appear to form a foam-like pattern when viewed on large scales. The relationship between voids and dark energy is particularly intriguing. As we've seen, voids expand faster than the cosmic average due to their underdensity, an effect that is amplified by dark energy. But some theorists have proposed a more direct connection, suggesting that the properties of dark energy might vary with density, behaving differently in voids than in denser regions. These inhomogeneous dark energy models propose that the equation of state of dark energy, which describes how its pressure relates to its density, might depend on the local environment. In voids, dark energy might have different properties, potentially explaining features like the cold spot and supervoid as regions where dark energy behaves unusually. While such models remain speculative, they highlight the potential of voids as laboratories for testing fundamental physics. By studying how voids evolve and how they affect their surroundings, astronomers can probe the nature of dark energy, the properties of gravity on the largest scales, and the formation of structure in the universe. Voids also serve as windows into the early universe. Because they contain so little matter, voids have evolved less than denser regions since the Big Bang. They preserve some of the initial conditions that seeded cosmic structure, making them valuable probes of the primordial density field. By studying the size and shape distribution of voids, astronomers can test whether the initial density fluctuations were indeed Gaussian, as predicted by the simplest inflationary models, or whether they had more complex statistical properties. The study of voids has led to the development of new statistical tools and techniques for analyzing cosmic structure. Traditional methods like the two-point correlation function, which measures how galaxies cluster together, are less effective for characterizing the emptiness of voids. Instead, astronomers use measures like the void probability function, which quantifies the likelihood of finding regions devoid of galaxies, and the genus statistic, which characterizes the topological properties of the cosmic web. These void statistics provide complementary information to traditional clustering measures, allowing for more rigorous tests of cosmological models. For example, the abundance of large voids is sensitive to the amount and properties of dark energy, while the shapes of voids can constrain modifications to Einstein's theory of gravity. The dynamics of matter around voids also provides a unique test of gravity. In general relativity, the motion of matter is determined by the curvature of space-time, which in turn is determined by the distribution of matter and energy. Alternative theories of gravity, such as modified Newtonian dynamics, MOND, or tensor vector scalar theory, TVES, make different predictions for how matter should move in low-density environments like voids. By measuring the velocities of galaxies around void boundaries, astronomers can test these different theories of gravity. Recent studies have found that the observed void dynamics are consistent with general relativity, placing constraints on alternative theories. However, more precise measurements of void dynamics from future surveys may reveal subtle deviations that could point to new physics. Voids also affect the overall statistics of the cosmic density field. The presence of large voids makes the distribution of matter in the universe more skewed than a Gaussian distribution. This non-Gaussianity is a natural outcome of gravitational evolution, as overdense regions become increasingly dense, while underdense regions can only become so empty. The density cannot be less than zero. This asymmetry leaves a distinctive statistical signature that can be measured in large galaxy surveys. The extreme rarity of structures like the supervoid, if confirmed, would represent the tail of this distribution, the most underdense regions in the cosmic density field. The probability of finding such extreme voids depends sensitively on the statistical properties of the primordial density fluctuations and their subsequent evolution, making the supervoid a valuable test case for cosmological models. Beyond their effects on matter and radiation, voids also influence the production and propagation of high-energy particles like cosmic rays. The magnetic fields that permeate the cosmic web are weaker in voids, allowing charged particles to travel more freely through these regions. This affects the observed distribution of cosmic ray arrival directions and energies, providing another potential probe of void properties. Similarly, voids may affect the propagation of gravitational waves, the ripples in spacetime predicted by Einstein's theory of general relativity and directly detected for the first time in 2015. As gravitational waves pass through regions of varying density, they are subtly affected by the gravitational potential, potentially carrying information about the large-scale structure they have traversed. The study of voids and their effects on the universe is still in its early stages, with many open questions and ongoing debates. The exact relationship between voids and the cold spot, the distribution of void sizes and shapes, the dynamics of matter within and around voids, and the connections between voids and fundamental physics are all active areas of research. As new telescopes and surveys come online in the coming decades, they will provide increasingly detailed observations of voids across cosmic time. These observations will allow astronomers to track how voids have evolved throughout the history of the universe, from the first protovoids that formed after the Big Bang to the vast empty regions we observe today. The discovery and study of the supervoid represents a milestone in this journey, challenging our understanding of cosmic structure and potentially pointing the way to new physics. Whether it proves to be an extraordinary statistical outlier or evidence for exotic phenomena, the supervoid reminds us that the emptiness between the stars and galaxies is as fundamental to the cosmos as the luminous objects that capture our imagination. In the next chapter, we will explore a more speculative question. What would it be like to live in the supervoid? How would the night sky appear to observers on a planet orbiting a star within this vast cosmic desert? And how might the development of astronomy and cosmology differ in such an isolated corner of the universe? Having explored various theories about the supervoid and its relationship to the cold spot, we now turn to the ongoing efforts to map this enormous cosmic structure in greater detail. Charting a region of relative emptiness spanning potentially billions of light years presents unique challenges, requiring astronomers to develop innovative techniques and utilize some of the most powerful telescopes and surveys available. The process of mapping cosmic voids is fundamentally different from mapping regions where matter is abundant. When astronomers study galaxy clusters or filaments, they are observing concentrations of luminous matter that emit radiation across the electromagnetic spectrum, but voids are defined by the absence of such matter. Mapping a void is akin to mapping the spaces between islands in an ocean, requiring us to define a structure by what is not there, rather than by what is. This fundamental challenge has necessitated the development of specialized techniques and observational strategies. In a sense, astronomers must learn to see the darkness, to recognize patterns in the absence of light, and to trace the boundaries where emptiness meets the cosmic web. It is a task that requires patience, precision, and a deep understanding of the statistical properties of cosmic structure. The primary method astronomers use to map cosmic voids is to survey the positions of galaxies in 3 dimensions. By identifying regions where galaxies are sparse or absent, they can trace the boundaries and internal structure of voids. This requires not just measuring the positions of galaxies on the sky, but also determining their distances from Earth, which is a much more challenging task. The most precise method for measuring galactic distances is through spectroscopic redshift surveys. When light from a distant galaxy reaches us, its wavelength is stretched, or redshifted, by the expansion of the universe. The amount of redshift is directly related to the galaxy's distance, following a relationship first discovered by Edwin Hubble in the 1920s. By analyzing the spectrum of light from a galaxy, astronomers can measure its redshift with great precision, providing an accurate estimate of its distance. Spectroscopic measurements involve passing the light from a galaxy through a prism or diffraction grating, splitting it into its component colors or wavelengths. This creates a spectrum that contains dark absorption lines or bright emission lines, corresponding to specific atoms and molecules in the galaxy. By measuring how much these lines are shifted from their rest wavelengths, astronomers can determine the galaxy's redshift and thus its distance. However, spectroscopic measurements are time-consuming, requiring significant telescope time for each individual galaxy. This makes it impractical to measure spectroscopic redshifts for all the galaxies in a large volume of space, particularly the fainter ones. For this reason, large-scale mapping projects often rely on photometric redshifts, which estimate distances based on how galaxies appear through different colored filters. While less precise than spectroscopic measurements, photometric redshifts allow astronomers to estimate distances for many more galaxies, providing a more complete, if less precise, map of the cosmic web. Photometric redshifts work on the principle that, as a galaxy's light is redshifted, its appearance through different colored filters changes in predictable ways. By observing a galaxy through multiple filters spanning the visible and near-infrared spectrum, astronomers can estimate its redshift by comparing its colors to those of galaxies with known spectroscopic redshifts. This method typically has an uncertainty of about 5 to 10% in the estimated distance, compared to less than 1% for spectroscopic redshifts. The trade-off between precision and sample size presents a challenge for void mapping. Spectroscopic surveys provide precise three-dimensional positions for a limited number of galaxies, potentially missing some of the structure of voids. Photometric surveys provide distances for many more galaxies, but with greater uncertainty, potentially blurring the boundaries of voids. The most comprehensive mapping efforts use a combination of both techniques, with spectroscopic redshifts providing a precise framework and photometric redshifts filling in the gaps. One of the most ambitious galaxy surveys used to study the supervoid is the Sloan Digital Sky Survey, SDSS. Beginning operations in 2000, this survey has mapped the positions and properties of more than 3 million galaxies and quasars. The SDSS uses a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, equipped with a 120-megapixel camera and spectrographs capable of measuring the spectra of hundreds of objects simultaneously. The SDSS has revolutionized our understanding of the large-scale structure of the universe. By systematically mapping a large fraction of the sky to significant depths, it has revealed the intricate patterns of the cosmic web in unprecedented detail. The survey operates by taking both imaging data, which shows the positions and brightness of galaxies on the sky, and spectroscopic data, which provides precise distances for a subset of these galaxies. The SDSS has been organized into a series of phases, each with specific scientific goals and observational strategies. The first phase, SDSS-I, operated from 2000 to 2005 and was primarily focused on mapping the large-scale structure of the universe. The second phase, SDSS-II, continued this work from 2005 to 2008, with additional emphasis on studying supernovae and the structure of the Milky Way. The third phase, SDSS-III, ran from 2008 to 2014 and included the Baryon Oscillation Spectroscopic Survey, BOSS, which was specifically designed to measure the cosmic distance scale with high precision. BOSS observed 1.5 million galaxies out to redshifts of 0.7, corresponding to a distance of about 8 billion light-years. This large, deep survey has been particularly valuable for studying cosmic voids, including the region around the cold spot. The SDSS has been instrumental in mapping the large-scale structure of the universe, revealing the complex network of filaments, walls, and voids that make up the cosmic web. Data from the SDSS has been used to identify and catalog thousands of cosmic voids, including some that are hundreds of millions of light-years across. These catalogs provide valuable context for understanding the supervoid, allowing astronomers to compare its properties to those of other large voids in the universe. For example, a study published in 2015 by Seshadri Nadathur and colleagues used data from BOSS to construct a catalog of cosmic voids. They identified nearly 800 voids, with typical sizes ranging from about 60 to 180 million light-years. The largest voids in their catalog approached 300 million light-years across, still significantly smaller than the purported size of the supervoid. This catalog helped establish a baseline for the expected distribution of void sizes in the universe, against which the supervoid could be compared. Another important survey for mapping the supervoid is the Pan-STARRS, Panoramic Survey Telescope and Rapid Response System, a wide-field imaging facility at the Haleakala Observatory in Hawaii. Pan-STARRS uses a 1.8-meter telescope equipped with a 1.4 billion pixel digital camera, one of the largest digital cameras ever built for astronomy. The survey has observed the entire sky visible from Hawaii in 5 different wavelength bands, from near ultraviolet to near infrared, providing photometric data for billions of stars and galaxies. Pan-STARRSONE began regular operations in 2010 and has since collected over 4 petabytes of data. The survey is designed to detect objects that change or move on timescales from hours to years, making it particularly useful for discovering asteroids, comets, variable stars, and supernovae. But its deep, multi-wavelength imaging of the static sky has also made it an invaluable resource for studying galaxies and mapping large-scale cosmic structures. Data from Pan-STARRSONE was crucial in the 2015 study by Istvan Zapudi and his colleagues that provided some of the strongest evidence for the supervoid. By combining Pan-STARRSONE data with infrared observations from the Wide Field Infrared Survey Explorer (WISE) satellite, they were able to estimate distances to millions of galaxies and identify a large underdensity aligned with the cold spot. According to their analysis, this underdensity extends about 1.8 billion light-years across and is centered at a distance of about 3 billion light-years from Earth. The WISE satellite, launched by NASA in 2009, observed the entire sky in 4 infrared wavelength bands. Its primary mission was to detect and characterize the most luminous galaxies in the universe, as well as nearby cool stars and asteroids. But the infrared data from WISE is also sensitive to the redshift of galaxies, making it valuable for estimating distances and mapping large-scale structure when combined with observations at other wavelengths. Zapudi's team used a technique called photometric redshift estimation to determine the approximate distances to millions of galaxies in the Pan-STARRSONE and WISE data. By analyzing how galaxies appear through different filters, they could estimate their redshifts and thus their distances. This allowed them to construct a 3-dimensional map of the galaxy distribution in the direction of the cold spot, revealing a significant underdensity at a distance of about 3 billion light-years. The supervoid they identified was not completely empty, but rather a region where the density of galaxies was about 20% lower than the cosmic average. While this might not seem like a dramatic underdensity, it was spread across an enormous volume of space, making it one of the largest known structures in the universe. The team estimated that the probability of finding such a large underdensity by chance was less than 1 in 20,000, suggesting that it was indeed an extraordinary cosmic feature. However, mapping a structure as vast and diffuse as the supervoid is not without challenges. Different surveys, using different observational techniques and different methods for estimating distances, can produce somewhat different maps of the same region. This has led to ongoing debates about the exact size, shape, and density profile of the supervoid. For example, a study published in 2017 by Ruari Mackenzie and his colleagues at Durham University used data from the Anglo-Australian Telescope to conduct a spectroscopic survey of galaxies in the direction of the cold spot. The Anglo-Australian Telescope, located at Siding Spring Observatory in Australia, has a 4-meter primary mirror and is equipped with the 2-degree field (TWAD-F) instrument, which can measure the spectra of up to 400 objects simultaneously across a 2-degree field of view. Mackenzie's team used TWAD-F to obtain precise spectroscopic redshifts for galaxies in the cold spot region, allowing them to map the 3-dimensional galaxy distribution with higher precision than was possible with photometric redshifts. Their analysis found a more complex structure than a single, enormous void. Instead, they detected several smaller voids and clusters at different distances, creating a complex pattern of underdensity and overdensity along our line of sight. This highlights a fundamental challenge in void mapping, defining where a void begins and ends. Unlike galaxy clusters, which have relatively well-defined boundaries, voids have fuzzy edges that gradually transition into filaments and walls. Different researchers may use different density thresholds to define void boundaries, leading to different estimates of void sizes and volumes. The concept of a void boundary is itself somewhat artificial, a human construct imposed on a continuous density field. In reality, the density of matter in the universe varies smoothly from place to place, with no abrupt transitions between void and non-void regions. Astronomers typically define voids as regions where the density falls below some threshold, often 20 to 50% of the cosmic average. But this threshold is somewhat arbitrary, and changing it can significantly affect the perceived size and shape of voids. Moreover, voids are not completely empty, but contain a sparse population of galaxies within them. These void galaxies are of great interest to astronomers because they evolve in relative isolation, free from the interactions and mergers that shape galaxies in denser regions. By studying the properties and distribution of galaxies within the supervoid, astronomers can gain insights into its internal structure and how it formed and evolved over cosmic time. Void galaxies tend to be smaller, bluer, and more isolated than galaxies in denser environments. They often show evidence of ongoing star formation, appearing relatively youthful compared to their counterparts in clusters and groups. This suggests that the environment within voids affects how galaxies evolve, perhaps by limiting the supply of gas for star formation or by reducing the frequency of interactions with other galaxies. The distribution of galaxies within voids is not random but shows subtle patterns and structures. Some void galaxies are arranged in tenuous filaments or sheets that thread through the emptiness, creating a hierarchy of structures within the larger void. Others are truly isolated, separated from their nearest neighbors by tens of millions of light-years. By mapping the positions and properties of these void galaxies, astronomers can probe the internal structure of voids and test theories of how these cosmic deserts form and evolve. Recent studies have indeed found that the supervoid is not uniformly empty, but contains internal substructure. Some regions within it are almost completely devoid of galaxies, while others contain tenuous filaments and isolated galaxy groups. This complexity makes it challenging to characterize the supervoid as a single, coherent structure and may explain some of the discrepancies between different observational studies. The shape of the supervoid is another area of ongoing investigation. Early analyses often assumed a roughly spherical shape for simplicity, but more detailed observations suggest a more complex geometry. Some studies indicate that the supervoid might be elongated along our line of sight, creating a tunnel-like structure that extends deep into space. Others suggest it might be part of a larger complex of interconnected voids and filaments, spanning an even greater volume than initially estimated. The possibility that the supervoid might be elongated along our line of sight is particularly intriguing, as it could affect how we interpret its rarity and significance. A void that appears very large from our vantage point might actually have a more moderate size when viewed from a different angle. This would make it less of a statistical outlier and potentially more consistent with the standard cosmological model. Understanding the three-dimensional shape of the supervoid is crucial for assessing its rarity and significance. A spherical void, 1.8 billion light-years in diameter, would be an extraordinary structure, far beyond what is expected in the standard cosmological model. But an elongated or irregular void might be less extreme, potentially more consistent with theoretical expectations. This highlights another challenge in void mapping: the limited information available from our single vantage point. We can only observe the universe from Earth, and we see distant objects not as they are now, but as they were when the light left them, which can be billions of years in the past. This makes it difficult to construct a complete, three-dimensional picture of cosmic structures, particularly on the largest scales. We must infer the three-dimensional shape of voids from their appearance in our two-dimensional sky, combined with distance estimates that have inherent uncertainties. To address these challenges, astronomers are employing increasingly sophisticated techniques for mapping and analyzing cosmic voids. One approach is to use computer algorithms to identify voids in galaxy survey data based on well-defined criteria. These void-finding algorithms can automatically detect underdense regions and characterize their properties, allowing for more objective and consistent void catalogs. Various types of void-finding algorithms have been developed, each with its own strengths and limitations. Some define voids as spherical regions devoid of galaxies above a certain brightness, while others use tessellation techniques to divide space into cells associated with individual galaxies, identifying voids as regions with larger cells. Still others define voids based on the dynamics of matter, looking for regions where galaxies are flowing away from a central point. The watershed void-finding algorithm, for example, treats the galaxy density field like a topographic map, identifying voids as basins that would fill with water if the map were flooded. This approach naturally accounts for the irregular shapes of voids and their hierarchical structure, where smaller voids nest within larger ones. Another approach, the Zobov, zones bordering on voidness algorithm, uses Voronoi tessellation to divide space based on galaxy positions, then identifies voids as connected regions of low density. Each void-finding algorithm has its own biases and assumptions, which can affect the resulting void catalogs. Some are more sensitive to the boundaries between voids and filaments, while others better capture the internal structure of voids. Some are designed to identify spherical voids, while others allow for more irregular shapes. By applying multiple void-finding algorithms to the same dataset and comparing the results, astronomers can build a more robust picture of void structures. This approach helps to distinguish genuine cosmic features from artifacts of particular analysis methods or observational limitations. Another important technique is to combine data from multiple surveys and wavelengths to create more comprehensive maps of the supervoid region. Each survey has its own strengths and limitations in terms of sky coverage, depth, and resolution. By integrating data from optical, infrared, radio, and other wavelengths, astronomers can build a more complete picture of the galaxy distribution and identify structures that might be missed in any single survey. For example, the 2-micron all-sky survey, 2MASS, observed the entire sky in near-infrared wavelengths, which are less affected by dust than optical wavelengths and can penetrate deeper into the galaxy distribution. The survey operated from 1997 to 2001, using 2 dedicated 1.3-meter telescopes, one in Arizona and one in Chile. 2MASS catalogued more than 470 million stars and 1.6 million galaxies, providing a comprehensive map of the infrared sky. The NRAO VLA Sky Survey, NVSS, mapped the sky in radio wavelengths, detecting galaxies and other radio sources that might not be visible at other wavelengths. Conducted with the Very Large Array in New Mexico between 1993 and 1996, the NVSS covered the entire sky north of declination, -40 degrees, and detected nearly 2 million radio sources. Radio observations are particularly valuable for void mapping because they are not affected by dust extinction and can detect active galaxies at great distances. By combining these surveys with optical data from SDSS and Pan-STAR-SOHN, astronomers can create multi-wavelength maps that reveal different aspects of the supervoid structure. Optical observations show the distribution of ordinary galaxies, infrared observations reveal dust-obscured galaxies, and radio observations highlight active galactic nuclei powered by supermassive black holes. Together, they provide a more complete census of the galaxy population and a more accurate map of the cosmic web. The development of machine learning techniques has also opened new possibilities for void mapping. These algorithms can be trained to recognize patterns in galaxy distributions that might not be obvious to human analysts or traditional void-finding algorithms. By learning from simulated cosmological data, where the true cosmic structures are known, machine learning models can become adept at identifying and characterizing voids in real observational data. One approach uses convolutional neural networks, a type of deep learning algorithm that has proven highly effective for image recognition tasks. These networks can be trained on simulated maps of the cosmic web, learning to identify voids of various sizes and shapes. When applied to real survey data, they can potentially detect voids with greater accuracy and consistency than traditional methods. Another machine learning approach uses density estimation techniques to model the galaxy distribution directly without imposing arbitrary thresholds or assumptions about void shapes. These methods can provide a more nuanced picture of the cosmic density field, revealing subtle patterns and structures that might be missed by simpler void-finding algorithms. The application of machine learning to void mapping is still in its early stages, but it holds great promise for advancing our understanding of these cosmic structures. As astronomical datasets grow larger and more complex, machine learning may become an essential tool for extracting meaningful insights and patterns from the cosmic web. In addition to mapping the distribution of galaxies, astronomers are also developing techniques to directly measure the dark matter distribution in and around voids. Dark matter, which makes up about 27% of the universe's mass energy content, does not emit or absorb light, but can be detected through its gravitational effects. By studying how the light from distant galaxies is subtly distorted as it passes near voids, a phenomenon known as weak gravitational lensing, astronomers can map the distribution of dark matter and test whether it follows the same pattern as the visible galaxies. Several ongoing and planned surveys are designed to measure weak lensing effects with unprecedented precision. The Dark Energy Survey, DES, which operated from 2013 to 2019, used a 570-megapixel camera on the 4-meter Blanco telescope in Chile to map 300 million galaxies over 5,000 square degrees of sky. DES data has been used to study the lensing effects of cosmic voids, providing insights into the distribution of dark matter in these underdense regions. Looking to the future, several upcoming telescopes and surveys promise to revolutionize our ability to map cosmic voids, including the supervoid. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, LSST, observing the entire southern sky every few nights for 10 years. With its 8.4-meter primary mirror and 3.2 billion pixel camera, the Rubin Observatory will detect billions of galaxies and provide unprecedented data on the large-scale structure of the universe. The Rubin Observatory's combination of depth, area, and temporal coverage will make it a powerful tool for mapping cosmic voids. By detecting fainter galaxies than previous surveys, it will reveal the tenuous structures within voids that have been largely invisible until now. By repeatedly observing the same regions of sky, it will allow astronomers to measure the subtle motions of galaxies over time, providing insights into the dynamics of void formation and evolution. Similarly, the Euclid Space Telescope, launched by the European Space Agency, is designed specifically to map the distribution of dark matter and dark energy throughout the universe. By observing billions of galaxies with both imaging and spectroscopy, Euclid will create the most detailed three-dimensional map of the universe to date, providing crucial insights into the formation and evolution of cosmic structures like the supervoid. Euclid operates from the second Lagrange point, the same location as the James Webb Space Telescope, about 1 million miles from Earth. From this vantage point, free from Earth's interfering atmosphere, it can make extremely precise measurements of galaxy shapes, positions, and redshifts. These observations will allow astronomers to map both the visible and dark matter distributions with unprecedented accuracy, potentially resolving many of the current debates about the supervoid's properties. The Nancy Grace Roman Space Telescope, planned for launch by NASA in the mid-2020s, will also contribute significantly to our understanding of large-scale cosmic structures. With its wide-field infrared camera, the Roman telescope will observe millions of galaxies with unprecedented precision, allowing for detailed studies of how galaxies are distributed within voids and how voids evolve over cosmic time. Like Euclid, the Roman telescope will operate from the second Lagrange point and will be equipped with a coronagraph, an instrument designed to block out the light from bright stars to enable the detection of faint nearby objects. While the coronagraph is primarily intended for studying exoplanets, the telescope's wide-field camera will be a powerful tool for cosmological studies, including mapping the supervoid region in greater detail than ever before. Another important future facility is the Square Kilometre Array, SKA, an international radio telescope project under construction in Australia and South Africa. When completed, the SKA will be the world's largest radio telescope, with a collecting area of 1 square kilometre spread across thousands of individual antennas. The SKA will observe the sky at low and mid-range radio frequencies, detecting billions of galaxies out to the edge of the observable universe. Radio observations from the SKA will complement optical and infrared surveys by detecting galaxies based on their hydrogen gas content rather than their stellar light. This will provide a different perspective on the galaxy distribution, potentially revealing structures within the supervoid that are gas-rich but star-poor. The SKA will also be able to measure the dynamics of galaxies through the Doppler shift of their radio emission, providing insights into how matter flows within and around voids. As these next-generation observatories come online, they will provide increasingly detailed maps of the supervoid, potentially resolving the ongoing debates about its size, shape, and significance. They may confirm that it is indeed an extraordinarily rare structure that challenges our understanding of cosmic evolution, or they might reveal it to be a complex arrangement of more typical cosmic structures that happen to create the appearance of a larger void when viewed from our particular vantage point. In either case, the ongoing efforts to map the supervoid represent a remarkable achievement in observational cosmology. From our tiny planet orbiting an ordinary star in an ordinary galaxy, we have been able to chart the distribution of matter across billions of light years, identifying not just where galaxies are concentrated, but also the vast empty regions between them. These maps of cosmic emptiness tell us as much about the universe's structure and evolution as maps of its densest regions, reminding us that in cosmology, absence can be as revealing as presence. As we continue to refine our maps of the supervoid, we come closer to understanding its true nature and significance. Is it an extreme statistical outlier, a rare but not impossible outcome of standard cosmic evolution? Is it evidence of exotic physics in the early universe, or the aftermath of a cosmic collision? Or is it simply a complex arrangement of more typical voids that happens to align with a rare fluctuation in the cosmic microwave background? The answer to these questions may have profound implications for our understanding of the cosmos. By mapping the void, we are not just charting an empty region of space, we are testing the foundations of our cosmological model and potentially opening windows onto new physics beyond the standard paradigm. In the next chapter, we will explore how voids like the supervoid influence the universe around them, affecting the properties of nearby galaxies, the flow of matter on large scales, and even the expansion of space itself. Cosmic evolution, or they might reveal it to be a complex arrangement of more typical cosmic structures that happen to create the appearance of a larger void when viewed from our particular vantage point. In either case, the ongoing efforts to map the supervoid represent a remarkable achievement in observational cosmology. From our tiny planet orbiting an ordinary star in an ordinary galaxy, we have been able to chart the distribution of matter across billions of light years, identifying not just where galaxies are concentrated, but also the vast empty regions between them. These maps of cosmic emptiness tell us as much about the universe's structure and evolution as maps of its densest regions, reminding us that in cosmology, absence can be as revealing as presence. As we continue to refine our maps of the supervoid, we come closer to understanding its true nature and significance. Is it an extreme statistical outlier, a rare but not impossible outcome of standard cosmic evolution? Is it evidence of exotic physics in the early universe, or the aftermath of a cosmic collision? Or is it simply a complex arrangement of more typical voids that happens to align with a rare fluctuation in the cosmic microwave background? The answer to these questions may have profound implications for our understanding of the cosmos. By mapping the void, we are not just charting an empty region of space, we are testing the foundations of our cosmological model and potentially opening windows onto new physics beyond the standard paradigm. In the next chapter, we will explore how voids like the supervoid influence the universe around them, affecting the properties of nearby galaxies, the flow of matter on large scales, and even the expansion of space itself. Having explored the discovery of the supervoid, its relationship to the cold spot, and various alternative explanations, we now venture into more speculative territory. If the supervoid is indeed as large as some observations suggest, and if it is truly connected to the cold spot in the cosmic microwave background, what might this tell us about the fundamental nature of our universe? In this chapter, we will explore some of the more daring theoretical ideas that have been proposed to explain these cosmic anomalies. One of the most intriguing possibilities is that the cold spot might be evidence of a collision between our universe and another bubble universe within a vast multiverse. This idea emerges from a theoretical framework called eternal inflation, developed by physicists including Alan Guth, Andrei Linde, and Alexander Vilenkin in the 1980s and 90s. According to the theory of cosmic inflation, our universe underwent a brief period of extraordinarily rapid expansion in its first fraction of a second. This expansion smoothed out the universe and stretched quantum fluctuations to macroscopic scales, seeding the temperature variations we observe in the cosmic microwave background. Eternal inflation extends this idea by proposing that inflation doesn't end everywhere at once. In some regions, inflation stops, allowing matter and energy to condense and eventually form galaxies and stars. These regions become bubble universes like our own, but in the space between these bubbles, inflation continues eternally, creating more and more bubble universes in an ever-expanding multiverse. If multiple bubble universes exist, they might occasionally collide with each other. Such a collision would leave a distinctive imprint in the cosmic microwave background of both universes, appearing as a circular pattern with a cold or hot spot surrounded by a ring of the opposite temperature. Some theoretical physicists, including Matthew Johnson, Richard Easter, and Anthony Aguirre, have suggested that the cold spot might be precisely such an imprint, a cosmic bruise from a collision with another universe. This hypothesis is certainly dramatic and would have profound implications for our understanding of the cosmos if confirmed. It would provide empirical evidence for the existence of other universes beyond our own, a concept that has long been the subject of theoretical speculation, but has seemed beyond the reach of observational testing. However, the bubble collision hypothesis faces several challenges. First, it's not clear that the cold spot's temperature profile matches exactly what would be expected from a bubble collision. Second, it predicts the existence of other similar features in the CMB, which have not been definitively observed. Most importantly, it requires accepting a complex theoretical framework, the multiverse, to explain a single anomalous observation, which many scientists regard as speculative. Another exotic explanation for the cold spot involves cosmic textures. According to some theories of particle physics, the universe underwent a series of phase transitions as it cooled after the Big Bang, similar to how water freezes into ice as the temperature drops. During these phase transitions, imperfections can form in the fabric of space-time, creating various types of topological defects, including textures. A cosmic texture would create a distinctive pattern in the cosmic microwave background, with a cold spot surrounded by a hot ring. As the texture collapses, it alters the gravitational potential in its vicinity, causing CMB photons passing through the region to lose or gain energy, creating the distinctive temperature pattern. This hypothesis was explored in detail by a team led by Neil Turok, who found that a texture model could provide a good fit to the observed temperature profile of the cold spot. The texture would have collapsed about 10 billion years ago, long after the cosmic microwave background was formed but well before the present day. The texture hypothesis is interesting because it connects the cold spot to fundamental physics in the early universe. If confirmed, it would provide evidence for a particular class of particle physics theories called grand unified theories, which seek to unify three of the four fundamental forces of nature, the electromagnetic, weak, and strong forces at high energies. However, like the bubble collision hypothesis, the texture model faces challenges. The types of particle physics theories that predict textures have become less favored as particle physics experiments have failed to find evidence for new forces and particles that these theories predict. Moreover, the texture hypothesis also predicts the existence of other similar features in the cosmic microwave background, which comprehensive searches have not definitively found. A third speculative explanation connects the supervoid and cold spot to modifications of gravity or dark energy. The standard cosmological model assumes that Einstein's theory of general relativity correctly describes gravity on all scales and that dark energy is a constant property of space itself. But what if these assumptions are not perfectly correct on the largest cosmic scales? Some alternative theories of gravity, such as modified Newtonian dynamics, MOND, or tensor vector scalar theory, TVS, propose modifications to Einstein's equations that become significant at very low accelerations, typical of the outer regions of galaxies or larger cosmic structures. These theories were initially developed to explain galactic rotation curves without invoking dark matter, but they might also have implications for the formation and evolution of cosmic voids. Similarly, some alternative dark energy models propose that the energy density of the vacuum is not constant, but changes over time or varies from place to place. These models, such as quintessence or K-essence, introduce a dynamic scalar field that evolves over cosmic history and could potentially create regions with unusual properties. If either gravity or dark energy behaves differently than assumed in the standard model, it could alter the formation and growth of cosmic structures. In particular, it might allow for the formation of larger voids than would be expected in the lambda CDM model, potentially explaining the existence of the supervoid. It might also enhance the integrated Sachs-Wolfe effect, strengthening the connection between the supervoid and the cold spot. However, these alternative theories face a significant challenge. They must not only explain the supervoid and cold spot, but also be consistent with the wealth of other cosmological observations that support the standard lambda CDM model. Any modification to gravity or dark energy must preserve the model's successful predictions for the overall expansion history of the universe, the pattern of temperature fluctuations in the cosmic microwave background, the clustering of galaxies on smaller scales, and many other observed phenomena. A fourth speculative idea is that the cold spot might be evidence of a special sort of topological defect called a cosmic string. Cosmic strings are one-dimensional defects that might have formed during phase transitions in the early universe, like extremely thin tubes of concentrated energy stretching across vast distances. If a cosmic string were to pass between us and the surface of last scattering, the region from which the cosmic microwave background originates, it would create a distinctive pattern in the CMB. The precise nature of this pattern would depend on whether the string is straight or forms a loop, its orientation, its tension, a measure of how massive the string is, and whether it is moving relative to us. Some theoretical work has suggested that a cosmic string loop could potentially create a pattern similar to the cold spot. If confirmed, this would be a remarkable discovery, as cosmic strings are predicted by some of the most fundamental theories in physics, including certain versions of string theory and grand unified theories. However, detailed analyses of the cold spot's temperature profile have generally found that it doesn't match well with what would be expected from a cosmic string. Moreover, cosmic strings should create multiple features in the cosmic microwave background, not just a single cold spot, and comprehensive searches for these signatures have not found compelling evidence for cosmic strings. A fifth and particularly speculative idea connects the cold spot to the possible existence of extra dimensions beyond the three spatial dimensions we directly experience. According to some theoretical frameworks, such as string theory, our universe might contain additional spatial dimensions that are curled up or compactified in such a way that they are not directly observable in everyday experiences. In some versions of these theories, the extra dimensions might vary in size from place to place in our observable universe. Regions where an extra dimension is slightly larger might have slightly different physical properties, potentially affecting the cosmic microwave background and the formation of structures like voids. While this idea is highly speculative and not widely pursued as an explanation for the cold spot, it illustrates how cosmic anomalies can inspire creative theoretical thinking, connecting observations of the largest structures in the universe to ideas about the fundamental nature of space and time. A sixth speculative explanation involves primordial non-Gaussianity. The standard inflationary model predicts that the initial density fluctuations in the early universe should follow a Gaussian random distribution. However, more complex inflationary models allow for small deviations from perfect Gaussianity. If the primordial fluctuations had a higher probability of extreme values than a Gaussian distribution would predict, this could increase the likelihood of very large voids forming later in cosmic history. The supervoid might then be a rare but not impossibly rare structure, consistent with a slightly non-Gaussian universe. This hypothesis is appealing because it requires relatively modest extensions to the standard cosmological model. It doesn't invoke exotic physics like cosmic strings or extra dimensions, but simply relaxes the assumption of perfect Gaussianity. Moreover, it makes testable predictions. If primordial non-Gaussianity explains the supervoid, we should be able to detect its signatures in detailed observations of the cosmic microwave background and large-scale structure. Current observations, including those from the Planck satellite, have placed tight constraints on primordial non-Gaussianity, finding that any deviations from Gaussianity are quite small. However, these constraints still allow for some level of non-Gaussianity that could potentially increase the probability of finding structures like the supervoid. A seventh speculative idea connects the cold spot to a concept called phantom dark energy. In the standard lambda CDM model, dark energy has a constant energy density as the universe expands. But in some alternative models, dark energy could be even more exotic, with an energy density that actually increases as the universe expands. This phantom dark energy would lead to an eventual Big Rip, where the accelerated expansion of the universe becomes so extreme that it tears apart galaxies, stars, planets, and eventually atoms themselves. Before reaching this extreme, phantom dark energy might create unusual features in the cosmic web, potentially including exceptionally large voids. Some theoretical work has explored whether variations in the properties of dark energy across the universe might create regions with different expansion histories. If the cold spot region happened to contain dark energy with slightly different properties, it might explain both the temperature decrement in the cosmic microwave background and the apparent underdensity of galaxies. However, like many exotic explanations, the phantom dark energy hypothesis faces the challenge of explaining why this effect would be confined to one region of the sky, rather than creating multiple cold spots or a more general pattern of anomalies in the cosmic microwave background. An eighth speculative idea proposes that the cold spot might be evidence of a violation of the cosmological principle itself. This principle, a cornerstone of modern cosmology, assumes that the universe is homogeneous and isotropic on large scales, meaning it has no preferred location or direction. But what if this assumption is not perfectly correct? Some cosmologists have suggested that we might live in a region of the universe with unusual properties, perhaps a larger scale underdensity beyond even the supervoid. This idea, sometimes called the local void hypothesis, has been proposed as a potential explanation for other cosmological puzzles, such as the tension between different measurements of the expansion rate of the universe. If we do live in an unusual region of the universe, it could affect our observations in complex ways. The cold spot and supervoid might be manifestations of this larger scale inhomogeneity, hints of cosmic structures that extend beyond the limits of our observations. This hypothesis is radical because it challenges a fundamental assumption of modern cosmology. If the universe is not homogeneous on the largest scales, it would require a significant revision of our cosmological models and could have implications for our understanding of the universe's origin, evolution, and ultimate fate. A ninth speculative idea connects the cold spot to the concept of cosmic variance. In a finite observable universe, we can only measure a limited sample of the cosmic structure. This means that there is an inherent statistical uncertainty in our measurements, known as cosmic variance. The cold spot and supervoid might be manifestations of this cosmic variance, rare but not impossible features in our particular observable patch of the universe. In an infinite universe governed by the same physical laws, there would be regions with even more extreme features, but they would be outside our observable horizon. This explanation is in some ways the most conservative, as it doesn't require new physics or violations of the cosmological principle. It simply acknowledges the limitations of our observations and the role of chance in shaping the particular region of the universe we can observe. As we've seen, there is no shortage of speculative ideas to explain the cold spot and supervoid. Each hypothesis has its strengths and weaknesses, and none has yet emerged as the definitive explanation. The debate continues within the cosmological community, with new observations and analyses constantly refining our understanding of these enigmatic cosmic features. What makes this topic so fascinating is the range of scales it connects, from the largest structures in the observable universe to the fundamental physics of the early cosmos. The cold spot and supervoid stand at the intersection of observational astronomy, theoretical physics, and cosmology, challenging us to synthesize our understanding across these disciplines. In the coming decades, new telescopes and surveys promise to provide much more detailed observations of both the cosmic microwave background and the large-scale structure of the universe. These observations may finally resolve the mystery of the cold spot and supervoid, either by confirming one of the existing hypotheses or by revealing new aspects of these cosmic anomalies that point to a different explanation altogether. Until then, the cold spot and supervoid remind us of the provisional nature of scientific knowledge. Even in cosmology, a field that has made remarkable progress in recent decades, there remain mysteries and anomalies that challenge our understanding. These challenges are not failures of science, but opportunities for growth and discovery, pushing us to refine our theories and expand our observational capabilities. In the next chapter, we will explore how astronomers are mapping the supervoid in greater detail, using increasingly sophisticated techniques to chart its size, shape, and internal structure. These maps may provide crucial clues to the nature of this cosmic enigma and its relationship to the cold spot in the cosmic microwave background. Having explored why the supervoid presents such a challenge to our standard cosmological model, we now turn to alternative explanations for the observations. Perhaps what we are seeing is not a single, enormous void that stretches the limits of what should be possible in our universe, but something else entirely. In this chapter, We will examine various alternative theories that have been proposed to explain the cold spot in the cosmic microwave background and the apparent void aligned with it. One of the first possibilities we must consider is that the observations might be affected by systematic errors or biases. Astronomical observations are extraordinarily challenging, requiring us to detect incredibly faint signals from vast distances, often through intervening material that can distort or contaminate the signal. Despite the remarkable advances in observational technology and techniques, there remains the possibility that what appears to be a supervoid is actually an artifact of the observational process. For example, the galaxy surveys used to identify the supervoid rely on various methods to estimate the distances to galaxies. The most precise method, spectroscopic redshift measurement, can only be applied to the brightest galaxies due to the large amounts of telescope time required. For fainter galaxies, astronomers often use photometric redshifts, which estimate distances based on how galaxies appear through different colored filters. While useful for surveying large numbers of galaxies, photometric redshifts are less precise than spectroscopic ones and can introduce systematic errors in the three-dimensional maps of galaxy distributions. Similarly, measurements of the cosmic microwave background must contend with various sources of foreground contamination, from dust and gas in our own galaxy to the effects of more distant galaxies and clusters. While sophisticated techniques have been developed to account for these contaminants, they are not perfect, and residual effects could potentially create artificial features in the CMB maps. However, it's important to note that both the cold spot in the cosmic microwave background and the supervoid have been observed by multiple instruments and analyzed by multiple teams using different techniques. The cold spot was first identified in the WMAP data and later confirmed by the Planck satellite, which had higher sensitivity and resolution. The supervoid has been detected in various galaxy surveys using different observational methods. This consistency across different observations makes it less likely that the features are merely artifacts of systematic errors. Another possibility is that what appears to be a single, enormous void might actually be a chance alignment of multiple smaller voids along our line of sight. In the hierarchical structure of the cosmic web, voids exist at various scales, from small bubbles a few tens of millions of light-years across, to larger voids hundreds of millions of light-years in extent. If several medium-sized voids happen to align along our line of sight, they might create the appearance of a single, larger void in galaxy surveys. This hypothesis gained some support from a study published in 2017 by a team led by Ruari Mackenzie at Durham University. Using data from the Anglo-Australian Telescope, they conducted a spectroscopic survey of galaxies in the direction of the cold spot. Their analysis suggested that the region contained several smaller voids at different distances, rather than a single enormous void. The combined effect of these voids on the cosmic microwave background might mimic what would be expected from a larger supervoid, even though no individual void was particularly extraordinary. This interpretation is appealing because it would not require us to invoke extraordinarily rare cosmic structures or modifications to the standard cosmological model. A chance alignment of several moderate-sized voids would be much less statistically improbable than a single void of the size initially attributed to the supervoid. Moreover, such an alignment would only appear unusual from our particular vantage point, preserving the cosmological principle that the universe should look roughly the same from all locations. However, other studies have questioned this interpretation. A detailed analysis by Istvan Sapudi and his colleagues argued that the galaxy distribution in the cold spot region is indeed consistent with a large, coherent underdensity rather than several disconnected voids. They suggested that the three-dimensional mapping techniques used in some studies might not be sensitive to the full extent of the supervoid, particularly if it has a complex shape or an irregular density profile. The debate about whether the supervoid is a single, coherent structure or a chance alignment of smaller voids highlights a broader challenge in observational cosmology. Our view of the universe is fundamentally limited by our vantage point. We can only observe the cosmos from one location, Earth, and we see distant objects not as they are now, but as they were when the light left them, which can be billions of years in the past for the most distant objects. This makes it difficult to construct a complete, three-dimensional picture of cosmic structures, particularly on the largest scales. A third possibility is that the cold spot might be a statistical fluke in the cosmic microwave background, unrelated to any intervening void or other structure. As we explored in previous chapters, the temperature fluctuations in the CMB are believed to follow a Gaussian random distribution, which means that extreme deviations from the average temperature are rare but not impossible. The cold spot is unusual, with a probability of occurring by chance of less than 1% in most analyses, but this does not definitively rule out the possibility that it is simply a rare fluctuation. If the cold spot is indeed just a statistical fluke, it would not require any exotic physics or extremely rare cosmic structures to explain. It would simply be an unusually cool region in the primordial radiation field, a rare outcome of the random processes that generated the initial density fluctuations in the early universe. The apparent alignment with a void or voids along our line of sight would then be a coincidence, albeit a remarkable one. This explanation has the virtue of simplicity, but many scientists find it unsatisfying. The cold spot is not just cool, it has a specific temperature profile, with a cold central region surrounded by a warmer ring that doesn't match what would be expected from a simple Gaussian fluctuation. Moreover, the coincidence of this rare feature in the CMB aligning with an unusual void along our line of sight seems too fortuitous to be merely chance. A fourth possibility involves more exotic physics. Perhaps the cold spot and the supervoid are telling us something fundamental about the nature of dark energy, dark matter, or gravity itself. Several alternative theories have been proposed that might more easily accommodate the existence of extremely large voids. For example, some modified gravity theories, which propose alternatives to Einstein's general relativity, predict different patterns of structure formation than the standard lambda CDM model. In these theories, the force of gravity might behave differently on the largest cosmic scales, potentially allowing for the formation of larger voids. Similarly, some alternative dark energy models, where the energy density of the vacuum changes over time or space, might enhance the growth of cosmic voids beyond what is expected in the standard model. Other exotic explanations involve primordial non-Gaussianity, the idea that the initial density fluctuations in the early universe were not perfectly Gaussian, as the simplest inflationary models predict. If the primordial fluctuations had a higher probability of extreme values, this could increase the likelihood of very large voids forming later in cosmic history. Some complex inflationary models do predict small deviations from Gaussianity, which could potentially be detected in detailed observations of the cosmic microwave background and large-scale structure. However, these exotic explanations face a significant challenge. They must not only account for the supervoid, but also be consistent with the wealth of other cosmological observations that support the standard lambda CDM model. Any modification to our understanding of dark energy, dark matter, or gravity must preserve the model's successful predictions for the overall expansion history of the universe, the pattern of temperature fluctuations in the cosmic microwave background, the clustering of galaxies on smaller scales, and many other observed phenomena. For this reason, most cosmologists are cautious about invoking new physics to explain the supervoid. They prefer to exhaust all conventional explanations first, following the principle of Occam's razor, which suggests that the simplest explanation consistent with the observations is usually the best. A fifth possibility is that the cold spot might be caused by a topological defect in the early universe, such as a cosmic texture. According to some theories of particle physics, the universe underwent a series of phase transitions as it cooled after the Big Bang, similar to how water freezes into ice as the temperature drops. During these phase transitions, imperfections can form in the fabric of space-time, creating various types of topological defects, including textures. A cosmic texture would create a distinctive pattern in the cosmic microwave background, with a cold spot surrounded by a hot ring, somewhat similar to what is observed in the cold spot region. Moreover, the probability of a texture being located along our line of sight to the supervoid would be independent of the probability of the void itself, potentially resolving the coincidence problem. This hypothesis was explored in detail by a team led by Neil Turok at the University of Cambridge. They found that a texture model could provide a good fit to the observed temperature profile of the cold spot. However, the texture hypothesis also predicts the existence of other similar features in the cosmic microwave background, and comprehensive searches have not found clear evidence for these. Furthermore, the types of particle physics theories that predict textures have become less favored, as particle physics experiments have failed to find evidence for new forces and particles that these theories predict. Perhaps the most exotic explanation proposed for the cold spot is that it might be evidence of a collision between our universe and another universe within a larger multiverse. According to some versions of eternal inflation theory, our universe might be just one of many bubble universes floating in a rapidly expanding background space. If two of these bubbles were to collide, the impact would leave an imprint in the cosmic microwave background of both universes. Computer simulations of such cosmic collisions suggest that they would create circular patterns in the CMB, with a cold or hot spot surrounded by a ring of the opposite temperature. This pattern bears some resemblance to the observed cold spot, leading some theorists to suggest that we might be seeing the aftermath of a cosmic collision. This hypothesis is certainly dramatic, and would have profound implications for our understanding of the cosmos, if confirmed. It would provide the first empirical evidence for the existence of other universes beyond our own, a concept that has long been the subject of theoretical speculation, but has seemed beyond the reach of observational testing. However, the bubble collision hypothesis faces several challenges. First, it's not clear that the cold spot's temperature profile matches exactly what would be expected from a bubble collision. Second, like the texture hypothesis, it predicts the existence of other similar features in the CMB, which have not been definitively observed. Finally, it requires accepting a complex theoretical framework, the multiverse, to explain a single anomalous observation, which many scientists regard as speculative at best. A sixth possibility, less exotic but still intriguing, is that the supervoid and cold spot might be related to large-scale bulk flows in the cosmos. According to the standard cosmological model, the universe should be largely homogeneous on the largest scales, with no preferred direction or location. However, some observations have suggested the existence of unexpected large-scale flows of galaxies, moving in a coherent direction across vast distances. These flows, if real, might indicate the presence of even larger structures beyond the supervoid, perhaps enormous underdensities or overdensities outside our observable universe that are exerting a gravitational influence on the regions we can see. The supervoid might be just one manifestation of these larger-scale inhomogeneities, a hint of cosmic structures that extend beyond the limits of our observations. This hypothesis connects to ongoing debates about the validity of the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. While this principle has been remarkably successful as a foundation for modern cosmology, some researchers have questioned whether it holds perfectly on all scales. If the universe does contain structures larger than the homogeneity scale predicted by the standard model, it could have significant implications for our understanding of cosmic evolution and the fundamental properties of the universe. A related idea is that the cold spot and supervoid might be connected to other large-scale anomalies observed in the cosmic microwave background. The cold spot is not the only feature in the CMB that has been flagged as potentially anomalous. Other observations, such as an apparent alignment of some of the largest-scale temperature patterns, an asymmetry between the northern and southern hemispheres of the sky, and a general lack of large-scale fluctuations, have all been noted as potentially unexpected within the standard cosmological model. If these various anomalies are connected, they might collectively point to some limitation or extension of the lambda CDM model. However, it's also possible that some or all of these apparent anomalies are statistical flukes or artifacts of how we analyze the data. The challenge for cosmologists is to determine which, if any, of these unusual features require explanations beyond the standard model. An additional consideration is the role of the integrated Sachs-Wolf effect, which we discussed in earlier chapters. This effect, whereby light from the cosmic microwave background changes frequency as it passes through evolving gravitational potentials, is well understood within the framework of general relativity and is expected to create small temperature changes in the CMB. Some researchers have suggested that the standard calculation of this effect might underestimate its magnitude in extreme cases, such as very large voids. If the integrated Sachs-Wolf effect is stronger than typically assumed for very large underdensities, it could potentially explain more of the cold spot's temperature decrement, reducing the need for exotic explanations or extremely rare statistical flukes. As we've seen, there are many potential explanations for the cold spot and the supervoid, ranging from observational artifacts and statistical flukes to exotic physics, and even other universes. Each hypothesis has its strengths and weaknesses, and none has yet emerged as the definitive explanation. The debate continues within the cosmological community, with new observations and analyses constantly refining our understanding of these enigmatic cosmic features. This diversity of explanations highlights an important aspect of modern cosmology, as our observations become increasingly precise and our theories more sophisticated. We are probing the boundaries of our understanding of the universe. The cold spot and supervoid stand at one such boundary, challenging us to determine whether they can be explained within our current theoretical framework or whether they point to new physics beyond the standard model. The resolution of this mystery will likely require a combination of approaches: more detailed observations of the cold spot region, both in the cosmic microwave background and in the distribution of galaxies; more sophisticated statistical analyses to better assess the significance of the anomalies; improved theoretical models of structure formation that can make more precise predictions about the expected distribution of void sizes; and perhaps new ways of testing exotic theories against multiple cosmological observations. In the coming decades, new telescopes and surveys promise to provide much more detailed maps of both the cosmic microwave background and the large-scale structure of the universe. These observations may finally resolve the mystery of the cold spot and the supervoid, either by confirming one of the existing hypotheses or by revealing new aspects of these cosmic anomalies that point to a different explanation altogether. As we await these future observations, the cold spot and supervoid remain enigmatic features of our cosmos, reminding us of how much we have learned about the universe and how much we still have to discover. They represent not just a puzzle to be solved, but an opportunity to deepen our understanding of the largest structures in the cosmos and the physical laws that govern their formation and evolution. In the next chapter, we will explore some of the more speculative theories about the cold spot and supervoid, venturing into the realm of theoretical physics to consider how these cosmic anomalies might connect to some of the most profound questions about the nature of our universe. Having explored the discovery of the supervoid and its relationship to the cold spot in the cosmic microwave background, we now turn to perhaps the most intriguing aspect of this cosmic mystery. According to our standard model of cosmology, a void of this size should be extraordinarily rare, if not impossible. To understand why, we need to delve into the fundamental principles that govern the formation and evolution of cosmic structure. The standard model of cosmology, formerly known as lambda cold dark matter, or lambda CDM, has been remarkably successful in explaining a wide range of astronomical observations. It combines the Big Bang theory with the concept of cosmic inflation, the presence of cold dark matter, and the existence of dark energy, represented by the cosmological constant lambda. This model provides a coherent framework for understanding how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. One of the central tenets of the lambda CDM model is that cosmic structures form through a process called gravitational instability. In the early universe, tiny quantum fluctuations, microscopic variations in the density of matter and energy, were stretched to macroscopic scales during the brief period of cosmic inflation. These fluctuations, now imprinted on the expanding universe, served as the seeds from which all cosmic structures would eventually grow. Regions that were slightly denser than average exerted a slightly stronger gravitational pull on their surroundings. This caused more matter to flow toward them, making them even denser and increasing their gravitational influence. Meanwhile, regions that were slightly less dense than average lost matter to their surroundings, becoming even less dense over time. This process of gravitational amplification, whereby initial density differences are enhanced, is the fundamental mechanism behind the formation of cosmic structure. The lambda CDM model makes specific predictions about the statistical properties of these initial density fluctuations. According to the theory of cosmic inflation, these fluctuations should follow what statisticians call a Gaussian random field. In simple terms, this means that the probability of finding a region with a particular density depends only on how far that density deviates from the cosmic average, with larger deviations being exponentially less likely. This Gaussian nature of the initial density field has profound implications for the structures that later form. It means that extremely overdense or underdense regions should be extraordinarily rare. The probability of finding such extreme regions decreases exponentially with the magnitude of the density deviation, following what mathematicians call a bell curve or Gaussian distribution. When we observe the cosmic microwave background, we are seeing a snapshot of these density fluctuations as they existed about 380,000 years after the Big Bang. The temperature variations in the CMB directly reflect the density variations in the early universe, with slightly hotter regions corresponding to slightly denser areas, and slightly cooler regions corresponding to slightly less dense areas. The pattern of temperature fluctuations in the cosmic microwave background aligns remarkably well with the predictions of the Lambda CDM model. The statistical properties of these fluctuations, such as their angular power spectrum and their approximate Gaussian distribution, provide strong evidence for the model's validity. This agreement between theory and observation is one of the great triumphs of modern cosmology. From these initial conditions, the Lambda CDM model allows us to predict how cosmic structures should evolve over time. Using sophisticated computer simulations, cosmologists can model the gravitational interactions of dark matter, ordinary matter, and the effects of dark energy on the expansion of the universe. These simulations produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe in large-scale galaxy surveys. One of the key predictions of these simulations is the distribution of void sizes. Voids form in regions that were initially slightly underdense. As the universe evolves, matter flows away from these regions toward nearby overdensities, making the voids larger and emptier over time. The expansion of the universe, particularly the accelerated expansion due to dark energy, further enlarges these voids. However, the growth of voids is limited by several factors. First, the initial underdensities from which they form are constrained by the Gaussian nature of the primordial density field. Extremely underdense regions are exponentially rare, so the starting points for the largest voids are limited. Second, the presence of surrounding structures, such as filaments and walls of galaxies, constrains how much a void can expand. Finally, the finite age of the universe limits how much time voids have had to grow. Taking all these factors into account, the Lambda CDM model predicts a specific distribution of void sizes. Small voids should be common, medium-sized voids less common, and very large voids increasingly rare. The probability of finding a void of a given size decreases exponentially as the size increases, much like the Gaussian distribution of the initial density fluctuations. Specifically, the model predicts that voids larger than about 1.2 billion light-years across should be extraordinarily rare in the observable universe. The probability of finding a void as large as the putative supervoid, spanning nearly 1.8 billion light-years according to some estimates, would be vanishingly small, on the order of 1 in several billion. This is why the discovery of the supervoid was so shocking to cosmologists. If confirmed, it would represent a structure that, according to our best theories, should not exist, or at least should be so rare that we would not expect to find one in our observable universe. It would be as if, in a world where the average adult human height is about 5 foot 9 inches, with a standard deviation of about 3 inches, you suddenly encountered someone who was 15 feet tall. Such an extreme outlier would challenge our understanding of human biology and growth. Another way to think about this is in terms of the cosmological principle, one of the fundamental assumptions of modern cosmology. This principle states that, on sufficiently large scales, the universe is homogeneous and isotropic. That is, it looks roughly the same in all directions and from all vantage points. The existence of a structure as large as the supervoid would challenge this principle, as it would represent a significant deviation from homogeneity on scales where the universe is expected to be smooth. The cosmological principle is not just a philosophical assumption, it is supported by extensive observational evidence. The uniformity of the cosmic microwave background, the consistent expansion rate measured in different directions, and the similar distribution of galaxies in different regions of the sky all point to a universe that is indeed homogeneous and isotropic on large scales. The characteristic scale at which the universe transitions from being lumpy and structured to being smooth and homogeneous is called the homogeneity scale. According to the Lambda CDM model, this scale is around 300 million light-years. Below this scale, we see the rich tapestry of the cosmic web, with its clusters, filaments, and voids. Above this scale, these structures average out, and the universe appears more and more uniform. A supervoid spanning 1.8 billion light-years would be 6 times larger than this homogeneity scale. It would represent a deviation from uniformity on scales where we expect the universe to be smooth. This is one of the reasons why the supervoid, if confirmed, would be so challenging for the standard cosmological model. To make this more concrete, let's consider some specific calculations. In the lambda-CDM model, the probability of finding a region with a given density contrast, that is, the relative difference between its density and the cosmic average, depends on the scale of the region. For small scales, large density contrasts are common. For large scales, even modest density contrasts become increasingly rare. For a region as large as the supervoid, with a density contrast of about 20% below the cosmic average, the probability of finding such a structure by chance in a Gaussian random field would be extremely small. Various calculations have estimated this probability to be anywhere from 1 in 10,000 to 1 in several billion, depending on the exact properties of the void and the specific assumptions made in the calculation. Even taking the more conservative estimate, this would make the supervoid an extreme statistical outlier, far beyond what would be expected in the observable universe. If the void is as large and as underdense as some observations suggest, it would represent a 5 or 6 sigma event, to use the language of statistics. This level of improbability is often used as a threshold for claiming the discovery of new physics in fields like particle physics. However, it's important to note that these calculations assume that the initial density field was perfectly Gaussian, as predicted by the simplest models of cosmic inflation. If there were slight deviations from Gaussianity in the primordial universe, as some more complex inflationary models allow, the probability of finding extremely large voids could be higher than these calculations suggest. Non-Gaussian features in the initial density field could arise from various physical processes in the very early universe. For example, certain types of interactions during inflation could produce non-Gaussian statistics with a higher probability of extreme density fluctuations. If our universe were described by such a model, the existence of the supervoid might be less problematic. Another complication is that the supervoid does not appear to be a single, spherical underdensity, but rather a complex structure, possibly composed of multiple voids or an elongated underdense region. This complexity makes it difficult to calculate exactly how rare such a structure would be in the lambda-CDM model. It's possible that a configuration of multiple smaller voids that happens to align along our line of sight might be more probable than a single, enormous void. Furthermore, we must consider the role of observation selection effects. Astronomical surveys have limited coverage and sensitivity, which means that we might be more likely to detect certain types of structures than others. It's possible that the apparent rarity of the supervoid is partly due to these selection effects, rather than reflecting its true cosmic significance. Despite these caveats, the supervoid remains a significant challenge for the standard cosmological model. If it is indeed as large as some estimates suggest, it would represent an extreme statistical outlier, pushing the boundaries of what the lambda-CDM model can comfortably accommodate. This raises a profound question. If the supervoid is real and is as large as it appears to be, what does this mean for our understanding of cosmic structure formation? There are several possible implications, each with far-reaching consequences for cosmology. One possibility is that the primordial density field was not perfectly Gaussian, as the simplest inflationary models predict. If the initial conditions of the universe included a higher probability of extreme density fluctuations, this could explain the existence of the supervoid without requiring a significant revision of the lambda-CDM model. Testing this hypothesis would require detailed observations of the cosmic microwave background and large-scale structure to look for other signs of primordial non-Gaussianity. Another possibility is that our understanding of how structure grows in the universe is incomplete. The lambda-CDM model includes specific assumptions about how dark matter, ordinary matter, and dark energy interact and evolve over cosmic time. If one or more of these assumptions is incorrect, it could affect our predictions for the distribution of void sizes. For example, if dark energy behaves differently than the cosmological constant assumed in the lambda-CDM model, it could alter the expansion history of the universe and the growth of cosmic structures. Some alternative dark energy models, such as quintessence or modified gravity theories, predict different patterns of structure formation that might more easily accommodate the existence of extremely large voids. Similarly, if dark matter has properties beyond those assumed in the standard cold dark matter model, such as a small amount of self-interaction or a non-negligible thermal velocity, it could affect how structures form and evolve. Some modified dark matter models predict different distributions of void sizes than the standard lambda CDM model. A more radical possibility is that the supervoid indicates a violation of the cosmological principle itself. Perhaps the universe is not as homogeneous on large scales as we have assumed. Some cosmologists have proposed that we might live in a region of the universe with unusual properties, perhaps a larger scale underdensity beyond even the supervoid. This idea, sometimes called the local void hypothesis, has been proposed as a potential explanation for other cosmological puzzles, such as the unexpectedly fast expansion rate of the nearby universe. However, most cosmologists are reluctant to abandon the cosmological principle, which has been a cornerstone of modern cosmology and is supported by a wide range of observations. The principle of cosmic homogeneity and isotropy is not just a simplifying assumption, it is a reflection of the fundamental symmetries we observe in the universe. To discard it would require extraordinarily compelling evidence, beyond even the supervoid. It's also possible that further observations will reveal that the supervoid is not as extreme as it initially appeared. The history of science is full of apparent anomalies that turned out to have conventional explanations once more data became available or more sophisticated analyses were conducted. For example, more detailed mapping of the galaxy distribution in the direction of the cold spot might reveal that the supervoid is not a single, enormous structure, but rather a complex arrangement of smaller voids and filaments that happens to create the appearance of a larger underdensity. Or it might show that the void is not as underdense as initial observations suggested, making it less of a statistical outlier. Similarly, more sophisticated analyses of the cold spot in the cosmic microwave background might reveal that it is less anomalous than previously thought. As we saw in the previous chapter, different statistical methods can yield different assessments of how unusual the cold spot truly is. It's possible that with better data and improved analytical techniques, the cold spot will be revealed to be a rare but not unprecedented feature of the cosmic microwave background. If this turns out to be the case, the supervoid would still be a fascinating cosmic structure, worthy of study for what it can tell us about the formation and evolution of the cosmic web. But it would not necessarily challenge our fundamental understanding of cosmology in the way that an extremely rare, statistically improbable structure would. On the other hand, if further observations confirm that the supervoid is indeed as large and as underdense as it appears to be, it would represent a significant challenge for the lambda CDM model. It would not necessarily invalidate the model entirely, which has been remarkably successful in explaining a wide range of astronomical observations. But it would suggest that the model is incomplete in some way, that there are aspects of cosmic structure formation that we don't fully understand. This would not be the first time that observations of large-scale structure have challenged the standard cosmological model. In the 1980s, the discovery of the Great Wall, a vast sheet of galaxies spanning over 500 million light-years, raised similar questions about the homogeneity of the universe. More recently, structures like the Sloan Great Wall, the Huge Large Quasar Group, and the giant GRB ring have all pushed the boundaries of what the lambda CDM model can comfortably accommodate. Each of these discoveries has prompted cosmologists to refine their understanding of structure, formation, and to develop more sophisticated models and simulations. The supervoid, if confirmed, would continue this tradition, pushing us to develop a more complete understanding of the cosmos. This is how science progresses, through the dynamic interplay of theory and observation. Theories make predictions, observations test those predictions, and when discrepancies arise, theories are refined or sometimes replaced. The story of the supervoid is still unfolding, but it has already provided a fascinating glimpse into this process of scientific discovery and the ongoing effort to understand the largest structures in our universe. As we continue to map the cosmos with increasingly powerful telescopes and surveys, we may discover more structures that challenge our current understanding. Each such discovery would provide a valuable opportunity to test and refine our cosmological models. Whether the supervoid ultimately proves to be a statistical fluke, a sign of new physics, or something in between, the quest to understand it has already enriched our understanding of the cosmos. In the next chapter, we will explore alternative explanations for the supervoid and the cold spot, considering both conventional and more exotic possibilities. We will examine whether the supervoid might be a statistical fluke, a manifestation of known physics, or perhaps a hint of something beyond the standard cosmological model. Through this exploration, we will gain a deeper appreciation for the complexity of cosmic structure and the challenges of studying the largest scales of our universe. To truly understand the significance of the billion light-year void, we must first understand the cosmic microwave background and the mysterious cold spot that led to the void's discovery. The cosmic microwave background radiation, often abbreviated as CMB, is the oldest light in the universe, a faint glow that fills all of space and comes to us from a time when the universe was in its infancy. The story of this ancient light begins about 380,000 years after the Big Bang. Before this time, the universe was an intensely hot, dense plasma, with electrons, protons, and photons all interacting constantly. Photons, the particles of light, could not travel far before being scattered by the free electrons in this plasma, making the early universe effectively opaque, like a dense fog. But as the universe expanded, it gradually cooled. When the temperature fell to about 3000 Kelvin, 2727 degrees Celsius, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms, a process astronomers call recombination. Suddenly, the photons that had been bouncing around in the cosmic fog were free to travel through space, unimpeded. The universe became transparent to light. These liberated photons have been traveling through space ever since, their wavelengths stretched by the expansion of the universe, from visible light to microwave radiation. When we detect this radiation today, we are seeing light that has been traveling for more than 13 billion years, a direct snapshot of the universe as it was at the moment of recombination. The existence of this cosmic microwave background was first predicted in the 1940s by Ralph Alpher and Robert Herman, who were working out the implications of the Big Bang theory. According to their calculations, if the universe began in an extremely hot, dense state and has been expanding and cooling ever since, there should be a faint residual glow permeating all of space, a relic of the universe's fiery beginning. Despite this prediction, the cosmic microwave background was discovered by accident. In 1964, two radio astronomers at Bell Laboratories, Arno Penzias and Robert Wilson, were using a sensitive microwave antenna to conduct experiments in satellite communications. They detected a persistent background noise, a faint hiss that seemed to come from all directions in the sky with equal intensity. After ruling out various potential sources of interference, including pigeon droppings on their antenna, they realized they had stumbled upon the cosmic microwave background radiation. The discovery of the CMB was a watershed moment in cosmology. It provided compelling evidence for the Big Bang theory, which until then had been just one of several competing models for the origin of the universe. Penzias and Wilson shared the 1978 Nobel Prize in Physics for their discovery, which transformed our understanding of cosmic history. At first, the cosmic microwave background appeared to be perfectly uniform, with the same temperature in all directions. This uniformity posed a puzzle for cosmologists. If the CMB was truly identical in all directions, then how did the complex structures we see in today's universe, from galaxies to galaxy clusters to the cosmic web, ever form? There needed to be some seeds, some initial irregularities, from which these structures could grow under the influence of gravity. The answer came in the early 1990s, when the Cosmic Background Explorer satellite, or COBE, made a groundbreaking discovery. It detected tiny variations in the temperature of the cosmic microwave background, differences of just 1 part in 100,000. These minute temperature fluctuations reflected small differences in the density of matter in the early universe, the seeds from which all cosmic structure would eventually grow. The COBE discovery was followed by increasingly precise measurements of these temperature fluctuations. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, mapped the cosmic microwave background with much greater resolution than COBE, revealing a detailed pattern of hot and cold spots across the sky. The Planck satellite, launched in 2009, provided an even more detailed map, the most precise picture of the infant universe ever created. These maps of the cosmic microwave background have become one of the most important tools in modern cosmology. By analyzing the statistical properties of the temperature fluctuations, scientists can determine fundamental parameters of our universe, including its age, its composition, its geometry, and its ultimate fate. The CMB has often been described as the cosmic Rosetta Stone, a key that allows us to decode the history and nature of our universe. One of the most remarkable things about the cosmic microwave background is how closely it matches the predictions of the Lambda CDM model, the standard model of cosmology. This model combines the Big Bang theory with the presence of cold, dark matter and dark energy, the mysterious force driving the accelerating expansion of the universe. When cosmologists simulate the evolution of a universe governed by the Lambda CDM model, they produce a pattern of temperature fluctuations in the cosmic microwave background that is strikingly similar to what we actually observe. But the match is not perfect. There are a few anomalies, regions where the observed pattern deviates from what the standard model predicts. Most of these anomalies are relatively minor and could plausibly be explained as statistical flukes, the cosmic equivalent of getting 10 heads in a row when flipping a coin. But one stands out as particularly significant: a large region in the constellation Eridanus, where the cosmic microwave background is unusually cool. This is the cold spot. The cold spot was first identified in the WMAP data in 2004 and later confirmed by the Planck satellite. It spans about 10 degrees on the sky, roughly 20 times the size of the full moon as seen from Earth. The temperature in this region is about 70 microkelvin cooler than the average temperature of the cosmic microwave background, which is approximately 2.7 Kelvin, minus 270.4 degrees Celsius. To appreciate the significance of the cold spot, we need to understand the statistical nature of the cosmic microwave background. According to the standard cosmological model, the temperature fluctuations in the CMB should follow what statisticians call a Gaussian distribution. This means that extreme deviations from the average, whether hot or cold, should be extremely rare, and the larger the deviation, the rarer it should be. When cosmologists analyzed the statistical properties of the cold spot, they found that it was a significant outlier. The probability of finding such a large cold region in a cosmic microwave background with a Gaussian distribution of temperature fluctuations was less than 1%. While not impossible, this was unusual enough to warrant further investigation. The search for an explanation for the cold spot led astronomers to consider various possibilities. Could it be a foreground effect, something between us and the cosmic microwave background that makes that region appear cooler? Could it be a statistical fluke, a rare but not impossible outcome in a universe described by the standard model? Or could it be evidence of new physics, a sign that our understanding of the cosmos is incomplete? One of the first explanations considered was that the cold spot might be caused by the integrated Sachs-Wolf effect, a phenomenon predicted by Einstein's theory of general relativity. According to this theory, light changes frequency as it passes through gravitational fields. When light from the cosmic microwave background passes through a large void, a region with less matter than average, it loses energy and becomes slightly cooler. This effect is most pronounced in a universe dominated by dark energy, like our own. For the integrated Sachs-Wolf effect to account for the cold spot, there would need to be an enormous void, a vast region nearly empty of galaxies, along our line of sight to that part of the cosmic microwave background. And indeed, as we explored in the previous chapter, evidence for just such a supervoid was found in galaxy surveys of the cold spot region. However, there was a problem with this explanation. When cosmologists calculated the expected temperature decrement that would be caused by the supervoid due to the integrated Sachs-Wolf effect, they found that it could account for only about 10 to 20% of the observed cold spot. Even the largest void allowed by the standard cosmological model would not be sufficient to fully explain the cold spot through this mechanism. This finding led to a puzzling situation. On the one hand, there appeared to be an unusually large void in the direction of the cold spot. On the other hand, this void did not seem capable of fully explaining the cold spot through known physics. It was as if two rare cosmic anomalies had coincidentally aligned, which itself would be an extraordinary coincidence. In the standard cosmological model, the integrated Sachs-Wolf effect works through a process called gravitational redshift. As the cosmic microwave background photons travel through space, they are affected by the changing gravitational potential of large-scale structures. When they fall into a gravitational well, such as a galaxy cluster, they gain energy and become slightly bluer. When they climb out of a gravitational well, they lose energy and become slightly redder. In a static universe, these effects would perfectly balance. A photon would gain exactly as much energy falling into a potential well as it would lose climbing out. But our universe is not static. It is expanding, and this expansion is accelerating due to dark energy. As a result, by the time a photon climbs out of a potential well, the well has become shallower, so the photon loses less energy climbing out than it gained falling in. This leads to a net blue shift and a slight increase in temperature. Conversely, when a photon passes through a void, a region with less matter than average, it experiences the opposite effect. It loses energy climbing out of the denser surroundings and into the void, and gains energy falling out of the void and back into denser regions. But because of the accelerating expansion, the void has grown larger by the time the photon exits, so it gains less energy exiting than it lost entering. This leads to a net redshift and a slight decrease in temperature. The magnitude of this effect depends on several factors: the size of the void, its depth, how much less dense it is compared to the cosmic average, its shape, and its distance from us. In general, the larger, deeper, and closer the void, the stronger the integrated Sachs-Wolf effect will be. When cosmologists calculated the expected temperature decrement from the supervoid identified in the direction of the cold spot, they found it would be about 7 to 15 microkelvin, depending on the precise properties of the void. This is significant, but it falls well short of the observed temperature decrement of about 70 microkelvin in the cold spot. This discrepancy led some cosmologists to propose a modification of the standard integrated Sachs-Wolf effect. Perhaps in the presence of exceptionally large voids, the effect is somehow amplified beyond what is predicted by the standard theory. This would require a modification to Einstein's theory of general relativity or to our understanding of dark energy, but it offered a potential resolution to the puzzle. Others suggested that the cold spot might be the result of not just one, but multiple voids along our line of sight. By stacking several underdense regions one behind the other, the cumulative effect on the cosmic microwave background might be sufficient to explain the cold spot. This hypothesis gained some support from galaxy surveys that found complex structures in the cold spot region, rather than a single, simple void. Yet another possibility was that the cold spot might be the result of two unrelated phenomena that happened to align. Perhaps there was indeed a supervoid along our line of sight, creating a modest temperature decrement through the integrated Sachs-Wolf effect. And perhaps, by chance, this aligned with an unusually cool region in the cosmic microwave background itself, a statistical fluke in the primordial temperature fluctuations. While the probability of both of these rare events occurring and aligning would be very small, it might still be more likely than some of the more exotic explanations. As astronomers continued to study the cold spot and the supervoid, they found that the relationship between the two was more complex than initially thought. The supervoid did not precisely align with the cold spot, as would be expected if it were the sole cause. Moreover, the shape of the temperature profile in the cold spot did not precisely match what would be expected from the integrated Sachs-Wolf effect alone. This led to more detailed investigations of the structure of both the cold spot and the supervoid. The cold spot, it turned out, had a distinctive temperature profile, with a cold central region surrounded by a slightly warmer ring, somewhat like a target or bullseye pattern. This profile did not match what would be expected from a simple void along the line of sight. Similarly, the supervoid itself appeared to have a complex structure. Rather than being a single spherical region of low density, it seemed to be composed of multiple underdense regions at different distances, possibly connected in a larger, elongated structure. This complexity made it difficult to calculate precisely what effect it would have on the cosmic microwave background. Another aspect of the cold spot that intrigued astronomers was its non-Gaussian nature. The standard cosmological model predicts that the temperature fluctuations in the cosmic microwave background should be Gaussian, meaning that they follow a specific statistical pattern. But the cold spot showed signs of non-Gaussianity, deviating from this expected pattern in subtle but significant ways. Non-Gaussianity in the cosmic microwave background is of great interest to cosmologists because it could indicate new physics in the early universe. The Standard Model of Cosmology, which includes a period of rapid expansion called inflation, predicts that the temperature fluctuations should be almost perfectly Gaussian. Deviations from Gaussianity could provide clues about the nature of inflation or suggest the presence of exotic phenomena in the early universe. One exotic explanation for the cold spot that gained attention was the possibility that it might be the imprint of a cosmic texture. In some theoretical models of the early universe, phase transitions can create topological defects in the fabric of space-time, somewhat like the defects that form in crystals as they cool. These defects, known as cosmic textures, would leave distinctive marks in the cosmic microwave background. Computer simulations showed that a cosmic texture could create a temperature profile similar to what is observed in the cold spot, with a cold central region surrounded by a warmer ring. However, textures should also create corresponding hotspots elsewhere in the sky, and these have not been definitively observed. Moreover, the probability of a texture of the right size and in the right location to explain the cold spot is very. To truly understand the significance of the billion light-year void, we must first understand the cosmic microwave background and the mysterious cold spot that led to the void's discovery. The cosmic microwave background radiation, often abbreviated as CMB, is the oldest light in the universe, a faint glow that fills all of space and comes to us from a time when the universe was in its infancy. The story of this ancient light begins about 380,000 years after the Big Bang. Before this time, the universe was an intensely hot, dense plasma, with electrons, protons, and photons all interacting constantly. Photons, the particles of light, could not travel far before being scattered by the free electrons in this plasma, making the early universe effectively opaque, like a dense fog. But as the universe expanded, it gradually cooled. When the temperature fell to about 3000 Kelvin, 2727 degrees Celsius, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms, a process astronomers call recombination. Suddenly, the photons that had been bouncing around in the cosmic fog were free to travel through space, unimpeded. The universe became transparent to light. These liberated photons have been traveling through space ever since, their wavelengths stretched by the expansion of the universe, from visible light to microwave radiation. When we detect this radiation today, we are seeing light that has been traveling for more than 13 billion years, a direct snapshot of the universe as it was at the moment of recombination. The existence of this cosmic microwave background was first predicted in the 1940s by Ralph Alpher and Robert Herman, who were working out the implications of the Big Bang theory. According to their calculations, if the universe began in an extremely hot, dense state and has been expanding and cooling ever since, there should be a faint residual glow permeating all of space, a relic of the universe's fiery beginning. Despite this prediction, the cosmic microwave background was discovered by accident. In 1964, two radio astronomers at Bell Laboratories, Arno Penzias and Robert Wilson, were using a sensitive microwave antenna to conduct experiments in satellite communications. They detected a persistent background noise, a faint hiss that seemed to come from all directions in the sky with equal intensity. After ruling out various potential sources of interference, including pigeon droppings on their antenna, they realized they had stumbled upon the cosmic microwave background radiation. The discovery of the CMB was a watershed moment in cosmology. It provided compelling evidence for the Big Bang theory, which until then had been just one of several competing models for the origin of the universe. Penzias and Wilson shared the 1978 Nobel Prize in Physics for their discovery, which transformed our understanding of cosmic history. At first, the cosmic microwave background appeared to be perfectly uniform, with the same temperature in all directions. This uniformity posed a puzzle for cosmologists. If the CMB was truly identical in all directions, then how did the complex structures we see in today's universe, from galaxies to galaxy clusters to the cosmic web, ever form? There needed to be some seeds, some initial irregularities, from which these structures could grow under the influence of gravity. The answer came in the early 1990s, when the Cosmic Background Explorer satellite, or COBE, made a groundbreaking discovery. It detected tiny variations in the temperature of the cosmic microwave background, differences of just 1 part in 100,000. These minute temperature fluctuations reflected small differences in the density of matter in the early universe, the seeds from which all cosmic structure would eventually grow. The COBE discovery was followed by increasingly precise measurements of these temperature fluctuations. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, mapped the cosmic microwave background with much greater resolution than COBE, revealing a detailed pattern of hot and cold spots across the sky. The Planck satellite, launched in 2009, provided an even more detailed map, the most precise picture of the infant universe ever created. These maps of the cosmic microwave background have become one of the most important tools in modern cosmology. By analyzing the statistical properties of the temperature fluctuations, scientists can determine fundamental parameters of our universe, including its age, its composition, its geometry, and its ultimate fate. The CMB has often been described as the cosmic Rosetta Stone, a key that allows us to decode the history and nature of our universe. One of the most remarkable things about the cosmic microwave background is how closely it matches the predictions of the Lambda CDM model, the standard model of cosmology. This model combines the Big Bang theory with the presence of cold, dark matter and dark energy, the mysterious force driving the accelerating expansion of the universe. When cosmologists simulate the evolution of a universe governed by the Lambda CDM model, they produce a pattern of temperature fluctuations in the cosmic microwave background that is strikingly similar to what we actually observe. But the match is not perfect. There are a few anomalies, regions where the observed pattern deviates from what the standard model predicts. Most of these anomalies are relatively minor and could plausibly be explained as statistical flukes, the cosmic equivalent of getting 10 heads in a row when flipping a coin. But one stands out as particularly significant: a large region in the constellation Eridanus, where the cosmic microwave background is unusually cool. This is the cold spot. The cold spot was first identified in the WMAP data in 2004 and later confirmed by the Planck satellite. It spans about 10 degrees on the sky, roughly 20 times the size of the full moon as seen from Earth. The temperature in this region is about 70 microkelvin cooler than the average temperature of the cosmic microwave background, which is approximately 2.7 Kelvin, minus 270.4 degrees Celsius. To appreciate the significance of the cold spot, we need to understand the statistical nature of the cosmic microwave background. According to the standard cosmological model, the temperature fluctuations in the CMB should follow what statisticians call a Gaussian distribution. This means that extreme deviations from the average, whether hot or cold, should be extremely rare, and the larger the deviation, the rarer it should be. When cosmologists analyzed the statistical properties of the cold spot, they found that it was a significant outlier. The probability of finding such a large cold region in a cosmic microwave background with a Gaussian distribution of temperature fluctuations was less than 1%. While not impossible, this was unusual enough to warrant further investigation. The search for an explanation for the cold spot led astronomers to consider various possibilities. Could it be a foreground effect, something between us and the cosmic microwave background that makes that region appear cooler? Could it be a statistical fluke, a rare but not impossible outcome in a universe described by the standard model? Or could it be evidence of new physics, a sign that our understanding of the cosmos is incomplete? One of the first explanations considered was that the cold spot might be caused by the integrated Sachs-Wolf effect, a phenomenon predicted by Einstein's theory of general relativity. According to this theory, light changes frequency as it passes through gravitational fields. When light from the cosmic microwave background passes through a large void, a region with less matter than average, it loses energy and becomes slightly cooler. This effect is most pronounced in a universe dominated by dark energy, like our own. For the integrated Sachs-Wolf effect to account for the cold spot, there would need to be an enormous void, a vast region nearly empty of galaxies, along our line of sight to that part of the cosmic microwave background. And indeed, as we explored in the previous chapter, evidence for just such a supervoid was found in galaxy surveys of the cold spot region. However, there was a problem with this explanation. When cosmologists calculated the expected temperature decrement that would be caused by the supervoid due to the integrated Sachs-Wolf effect, they found that it could account for only about 10 to 20% of the observed cold spot. Even the largest void allowed by the standard cosmological model would not be sufficient to fully explain the cold spot through this mechanism. This finding led to a puzzling situation. On the one hand, there appeared to be an unusually large void in the direction of the cold spot. On the other hand, this void did not seem capable of fully explaining the cold spot through known physics. It was as if two rare cosmic anomalies had coincidentally aligned, which itself would be an extraordinary coincidence. In the standard cosmological model, the integrated Sachs-Wolfe effect works through a process called gravitational redshift. As the cosmic microwave background photons travel through space, they are affected by the changing gravitational potential of large-scale structures. When they fall into a gravitational well, such as a galaxy cluster, they gain energy and become slightly bluer. When they climb out of a gravitational well, they lose energy and become slightly redder. In a static universe, these effects would perfectly balance. A photon would gain exactly as much energy falling into a potential well as it would lose climbing out. But our universe is not static. It is expanding, and this expansion is accelerating due to dark energy. As a result, by the time a photon climbs out of a potential well, the well has become shallower, so the photon loses less energy climbing out than it gained falling in. This leads to a net blue shift and a slight increase in temperature. Conversely, when a photon passes through a void, a region with less matter than average, it experiences the opposite effect. It loses energy climbing out of the denser surroundings and into the void, and gains energy falling out of the void and back into denser regions. But because of the accelerating expansion, the void has grown larger by the time the photon exits, so it gains less energy exiting than it lost entering. This leads to a net redshift and a slight decrease in temperature. The magnitude of this effect depends on several factors: the size of the void, its depth, how much less dense it is compared to the cosmic average, its shape, and its distance from us. In general, the larger, deeper, and closer the void, the stronger the integrated Sachs-Wolfe effect will be. When cosmologists calculated the expected temperature decrement from the supervoid identified in the direction of the cold spot, they found it would be about 7 to 15 microkelvin, depending on the precise properties of the void. This is significant, but it falls well short of the observed temperature decrement of about 70 microkelvin in the cold spot. This discrepancy led some cosmologists to propose a modification of the standard integrated Sachs-Wolfe effect. Perhaps in the presence of exceptionally large voids, the effect is somehow amplified beyond what is predicted by the standard theory. This would require a modification to Einstein's theory of general relativity or to our understanding of dark energy, but it offered a potential resolution to the puzzle. Others suggested that the cold spot might be the result of not just one, but multiple voids along our line of sight. By stacking several underdense regions one behind the other, the cumulative effect on the cosmic microwave background might be sufficient to explain the cold spot. This hypothesis gained some support from galaxy surveys that found complex structures in the cold spot region, rather than a single, simple void. Yet another possibility was that the cold spot might be the result of two unrelated phenomena that happened to align. Perhaps there was indeed a supervoid along our line of sight, creating a modest temperature decrement through the integrated Sachs-Wolfe effect. And perhaps, by chance, this aligned with an unusually cool region in the cosmic microwave background itself, a statistical fluke in the primordial temperature fluctuations. While the probability of both of these rare events occurring and aligning would be very small, it might still be more likely than some of the more exotic explanations. As astronomers continued to study the cold spot and the supervoid, they found that the relationship between the two was more complex than initially thought. The supervoid did not precisely align with the cold spot, as would be expected if it were the sole cause. Moreover, the shape of the temperature profile in the cold spot did not precisely match what would be expected from the integrated Sachs-Wolfe effect alone. This led to more detailed investigations of the structure of both the cold spot and the supervoid. The cold spot, it turned out, had a distinctive temperature profile, with a cold central region surrounded by a slightly warmer ring, somewhat like a target or bullseye pattern. This profile did not match what would be expected from a simple void along the line of sight. Similarly, the supervoid itself appeared to have a complex structure, Rather than being a single spherical region of low density, it seemed to be composed of multiple underdense regions at different distances, possibly connected in a larger, elongated structure. This complexity made it difficult to calculate precisely what effect it would have on the cosmic microwave background. Another aspect of the cold spot that intrigued astronomers was its non-Gaussian nature. The standard cosmological model predicts that the temperature fluctuations in the cosmic microwave background should be Gaussian, meaning that they follow a specific statistical pattern. But the cold spot showed signs of non-Gaussianity, deviating from this expected pattern in subtle but significant ways. Non-Gaussianity in the cosmic microwave background is of great interest to cosmologists because it could indicate new physics in the early universe. The standard model of cosmology, which includes a period of rapid expansion called inflation, predicts that the temperature fluctuations should be almost perfectly Gaussian. Deviations from Gaussianity could provide clues about the nature of inflation or suggest the presence of exotic phenomena in the early universe. One exotic explanation for the cold spot that gained attention was the possibility that it might be the imprint of a cosmic texture. In some theoretical models of the early universe, phase transitions can create topological defects in the fabric of space-time, somewhat like the defects that form in crystals as they cool. These defects, known as cosmic textures, would leave distinctive marks in the cosmic microwave background. Computer simulations showed that a cosmic texture could create a temperature profile similar to what is observed in the cold spot, with a cold central region surrounded by a warmer ring. However, textures should also create corresponding hotspots elsewhere in the sky, and these have not been definitively observed. Moreover, the probability of a texture of the right size and in the right location to explain the cold spot is very small. An even more exotic possibility was that the cold spot might be evidence of a collision between our universe and another bubble universe within a larger multiverse. According to some versions of inflationary theory, our universe might be just one of many bubble universes that nucleated within an eternally inflating background. If two of these bubbles were to collide, the impact would leave an imprint in the cosmic microwave background, potentially creating a pattern similar to the cold spot. This hypothesis was particularly intriguing because it offered a way to test ideas about the multiverse, which had previously been considered beyond the reach of empirical science. If the cold spot were indeed the result of a bubble collision, it would provide evidence for the existence of other universes beyond our own, a truly revolutionary discovery. However, like the cosmic texture hypothesis, the bubble collision idea faced challenges. The expected signature of a bubble collision would be a circular pattern with specific statistical properties, and it was not clear that the cold spot matched these expectations. Moreover, while a bubble collision would indeed create a cold or hot spot in the cosmic microwave background, it would require a remarkable coincidence for this to align with a supervoid along the same line of sight. As astronomers continued to debate these various explanations for the cold spot, another possibility remained on the table, that it might simply be a statistical fluke, a rare but not impossible fluctuation in the cosmic microwave background. After all, even in a perfectly Gaussian random field, there is a small probability of finding regions as extreme as the cold spot. The debate over the statistical significance of the cold spot has been complex and nuanced. Different analyses, using different statistical techniques and different definitions of what constitutes an anomaly, have reached different conclusions about how unlikely the cold spot would be in a universe described by the standard cosmological model. One particularly thorough analysis was published in 2015 by a team led by Seshadri Nadatha. They used a technique called the reversed spherical Mexican hat wavelet transform to identify unusual spots in the cosmic microwave background and assess their statistical significance. According to their analysis, the cold spot was indeed unusual, but not extraordinarily so. They estimated that the probability of finding such a feature by chance was about 1 to 2%, which means that while it is an outlier, it is not necessarily beyond what would be expected from random statistical fluctuations. Other analyses have come to different conclusions, some finding the cold spot to be more statistically significant, others less so. The lack of consensus reflects the challenging nature of statistical analysis when dealing with complex, non-uniform datasets like the cosmic microwave background. Different statistical methods can yield different results, and there is often room for judgment in how the analysis is conducted. This debate about the statistical significance of the cold spot highlights an important aspect of modern cosmology. As our observations become more precise and our datasets more vast, we are able to detect increasingly subtle features and patterns. But with this increased sensitivity comes an increased risk of finding apparent anomalies that are simply the result of random chance, what statisticians call false positives. In science, there is a natural tendency to focus on unusual or unexpected results, as these can lead to new discoveries and insights. But this focus can sometimes lead to an overemphasis on apparent anomalies that may not be statistically significant. This is why rigorous statistical analysis is so important in cosmology, and why scientists approach claims of cosmic anomalies with a healthy dose of skepticism. The cold spot is a particularly challenging case because it involves not just one apparent anomaly, but two: an unusually cool region in the cosmic microwave background and an unusually large void along the same line of sight. The coincidence of these two rare features suggests a connection between them, but the known physical mechanism that could link them, the integrated Sachs-Wolfe effect, does not seem sufficient to fully explain the relationship. This has led some cosmologists to propose modifications to our understanding of how the cosmic microwave background interacts with large-scale structures. Perhaps there are additional effects, beyond the standard integrated Sachs-Wolfe effect, that could enhance the impact of voids on the CMB temperature. Or perhaps our models of void evolution and structure need to be refined to better account for the observed temperature decrement. One possibility is that our understanding of dark energy, the mysterious force driving the accelerating expansion of the universe, is incomplete. The strength of the integrated Sachs-Wolfe effect depends on the properties of dark energy, particularly its equation of state, which describes how its density changes as the universe expands. If dark energy behaves differently than assumed in the standard cosmological model, it could potentially enhance the effect of voids on the cosmic microwave background. Another possibility is that gravity itself might behave differently on the largest cosmic scales. Einstein's theory of general relativity has been extraordinarily successful in describing gravity in a wide range of contexts, from the solar system to binary pulsars to gravitational waves. But it has not been directly tested on scales as large as the supervoid. If general relativity needs modification on these extreme scales, it could alter our predictions for how voids affect the cosmic microwave background. These ideas are speculative, and most cosmologists remain cautious about invoking new physics to explain the cold spot. The history of science is full of apparent anomalies that were eventually explained within the existing theoretical framework. Once more data became available, or more sophisticated analyses were conducted, it is possible that the cold spot will follow this pattern, and that further observations and analyses will reveal it to be compatible with the standard cosmological model. Indeed, some recent studies have suggested that the cold spot may be less anomalous than previously thought. A detailed analysis of the Planck data, published in 2019, found that when certain systematic effects are properly accounted for, the statistical significance of the cold spot decreases. According to this analysis, the probability of finding such a feature by chance might be as high as 5 to 10%, making it much less of an outlier. Similarly, more detailed analyses of the galaxy distribution in the direction of the cold spot have revealed a complex structure, with multiple voids and clusters at different distances. This complexity makes it difficult to calculate precisely what effect these structures would have on the cosmic microwave background, and it is possible that when fully accounted for, they might explain more of the cold spot than previous analyses suggested. The debate about the nature and significance of the cold spot and the supervoid continues to evolve as new data becomes available and new analytical techniques are developed. Astronomers are using increasingly sophisticated methods to map the distribution of galaxies in 3 dimensions, to model the effects of cosmic structures on the cosmic microwave background, and to analyze the statistical properties of the CMB itself. One promising avenue of research involves cross-correlating the cosmic microwave background with maps of the galaxy distribution. By examining how the CMB temperature relates to the presence of voids and clusters across the entire sky, astronomers can test theories about the integrated Sachs-Wolfe effect and other potential interactions between the CMB and cosmic structures. These studies may provide insights into the cold spot mystery by placing it in a broader context. Another approach is to search for other unusual regions in the cosmic microwave background and the galaxy distribution. If the cold spot and the supervoid are truly unique, it would strengthen the case that they are related and that they might require an explanation beyond the standard cosmological model. But if similar features are found elsewhere in the sky, it would suggest that they are simply unusual but not unprecedented outcomes of known physical processes. As we ponder the mystery of the cold spot, it is worth reflecting on the remarkable progress that has brought us to this point. Just a few decades ago, we had no direct image of the cosmic microwave background, no detailed maps of the large-scale structure of the universe, and only a rudimentary understanding of how cosmic structures form and evolve. Today, we are able to detect temperature variations of a few millionths of a degree in the cosmic microwave background and map the three-dimensional positions of millions of galaxies across billions of light years. This progress has allowed us to test the standard cosmological model with unprecedented precision. The model has passed these tests with flying colors, successfully predicting the detailed pattern of temperature fluctuations in the cosmic microwave background, the clustering of galaxies on large scales, and many other observable phenomena. The existence of a few anomalies like the cold spot does not invalidate this remarkable success, but it does remind us that our understanding of the cosmos is still incomplete. The cold spot mystery also highlights the interconnected nature of cosmic phenomena. The temperature of the cosmic microwave background, the distribution of galaxies in space, the expansion of the universe, and the nature of dark energy are all linked in complex ways. To fully understand any one of these aspects, we must understand how it relates to the others. The quest to explain the cold spot has led astronomers to explore these connections, deepening our understanding of the cosmic web and its evolution. As we gaze into the cold spot, we are looking at one of the most puzzling regions of the cosmos, a place where the absence of warmth in the cosmic microwave background aligns with the absence of galaxies in the cosmic web. Whether this alignment is a cosmic coincidence, a manifestation of known physics, or a hint of something new and unexpected remains to be determined. But the journey to answer this question is leading us to a deeper understanding of the universe in which we live. In the next chapter, we will explore why a void of this enormous size is so puzzling from a theoretical perspective, and what it might mean for our understanding of cosmic structure formation. We will delve into the standard model of cosmology and examine why structures like the supervoid challenge our current theories, pushing us to refine and possibly revise our picture of the cosmos. The story of the billion light-year void begins not with emptiness, but with a subtle anomaly in the oldest light in the universe. This light, known as the cosmic microwave background radiation, or CMB, has been traveling through space for over 13 billion years. It carries within it the imprint of the universe, as it was just 380,000 years after the Big Bang, long before the first stars or galaxies had formed. The cosmic microwave background is, in many ways, the most perfect natural phenomenon we have ever observed, a nearly uniform sea of microwave radiation coming from all directions in the sky, varying in temperature by less than 1 part in 100,000. It is precisely this remarkable uniformity that makes even the smallest deviations so interesting to cosmologists. These tiny temperature variations, just millionths of a degree, reflect the seeds of cosmic structure, the earliest hints of the clusters, filaments, and voids that would eventually form. By studying these variations, scientists can learn about the fundamental properties of our universe, including its composition, age, and the laws that govern its evolution. In the early 2000s, a space mission called the Wilkinson Microwave Anisotropy Probe, or WMAP, set out to map these minute temperature variations with unprecedented precision. Launched in June 2001, WMAP orbited a point in space called the Second Lagrange Point, or L2, 1 million miles from Earth. This location, where the gravitational forces of the Earth and Sun balance in such a way that a spacecraft can maintain a stable position, provided an ideal vantage point from which to observe the cosmic microwave background, free from Earth's interfering warmth and radio emissions. The WMAP satellite was designed specifically to capture the faintest whispers of the cosmic microwave background. Its unique design featured 2 back-to-back telescopes that collected microwave radiation from 2 different parts of the sky simultaneously. By comparing these signals, the satellite could eliminate many sources of instrumental noise and systematic error, allowing it to measure temperature differences as small as 1/1,000,000th of a degree. The satellite's sensitive detectors operated at 5 different frequency bands, enabling astronomers to distinguish the cosmic microwave background from foreground sources like our own galaxy. For years, WMAP scanned the entire sky, measuring the temperature of the cosmic microwave background radiation with exquisite sensitivity. The data it gathered was translated into a map, a representation of the entire observable universe as it appeared in its infancy. Most of what WMAP observed matched perfectly with the predictions of the Standard Model of Cosmology, a theoretical framework that combines the Big Bang theory with the concept of cosmic inflation and the presence of dark matter and dark energy. But in 2004, a team of scientists led by Lawrence Rudnick at the University of Minnesota noticed something unusual in the WMAP data. In a region of the sky, in the direction of the constellation Eridanus, there was a particularly large cold spot, an area where the cosmic microwave background radiation was slightly cooler than expected. This temperature difference was tiny, just 70 millionths of a degree cooler than the average, but it extended across a region of sky roughly 10 degrees in diameter, about 20 times the size of the full moon, as seen from Earth. The region, which came to be known simply as the cold spot, stood out not just because it was cool, but because of its peculiar combination of size and coolness. Smaller cool spots were common in the cosmic microwave background, as were larger areas with less extreme temperature deviations. But according to the standard cosmological model, a spot this large and this cool should be exceedingly rare. What made this cold spot particularly intriguing was not just its size, but its statistical improbability. According to the standard cosmological model, variations in the temperature of the cosmic microwave background should follow what statisticians call a Gaussian distribution. In simple terms, extreme deviations should be extremely rare. The cold spot observed by WMAP was so extreme that it had less than a 1% chance of occurring randomly in a universe described by the standard model. To understand this better, imagine flipping a coin 1,000 times. You expect to get roughly 500 heads and 500 tails, with small variations from this average being common and large variations being rare. If you flipped 900 heads and only 100 tails, you would be justified in suspecting that the coin was biased, or that something unusual was happening. The cold spot represented a similar statistical anomaly in the cosmic microwave background. At first, many astronomers suspected the cold spot might be an observational error, a flaw in the WMAP instrumentation, or perhaps contamination from some closer source of microwave radiation. Space is full of objects and phenomena that emit or absorb radiation at the frequencies measured by WMAP, from dust in our own galaxy to distant clusters of galaxies. Any of these could potentially create a false signal in the data. Other astronomers attempted to identify specific sources that might explain the anomaly. They examined maps of the sky at different wavelengths, looking for anything unusual in the direction of the cold spot. They considered known sources of microwave emission, from synchrotron radiation produced by electrons spiraling in magnetic fields to thermal emission from dust grains. They even investigated whether the solar system might be moving through a local void that could produce a similar effect. However, subsequent observations with different instruments, including the Planck satellite, launched by the European Space Agency in 2009, confirmed the existence of the cold spot. It was no mirage, no artifact of flawed measurements. It was a real feature of the cosmic microwave background, a genuine anomaly that demanded explanation. The Planck satellite represented the next generation of cosmic microwave background observations after WMAP. With higher sensitivity and better angular resolution, Planck provided the most detailed map of the cosmic microwave background to date. When the Planck team analyzed their data, they not only confirmed the existence of the cold spot, but were able to study its properties in greater detail. The new observations strengthened the case that the cold spot was a real feature of the cosmic microwave background and not a result of observational error. One of the most striking properties of the cold spot revealed by Planck was its complex internal structure. Rather than being uniformly cold, it contained a central cold region surrounded by a ring of slightly warmer areas, creating a pattern that some astronomers compared to ripples in a pond. This distinctive profile, which statisticians call a non-Gaussian morphology, made the cold spot even more unusual and less likely to be a random fluctuation in the cosmic microwave background. The question that now faced astronomers was simple. What could cause such a large, cool region in the cosmic microwave background? The answer, it would turn out, might lie not in the early universe where the CMB originated, but in the vast expanses of space between that ancient light and our telescopes. As the cosmic microwave background radiation travels through space on its long journey to our instruments, it passes through regions of varying density. According to Einstein's theory of general relativity, light loses energy when it climbs out of a gravitational well. This energy loss manifests as a slight decrease in the light's frequency, a phenomenon known as gravitational redshift. For the cosmic microwave background, this means that radiation passing through a region with less mass than average, such as a void, would be slightly cooler than radiation passing through a region with more mass than average. Conversely, light gains energy when it falls into a gravitational well, resulting in a slight increase in frequency, or a gravitational blue shift. As the universe expands, the gravitational wells associated with large-scale structures like galaxy clusters become shallower over time. This means that the cosmic microwave background photons gain less energy falling in than they lose climbing out, resulting in a net redshift and a corresponding temperature decrease. This effect, known as the integrated Sachs-Wolf effect, or ISW effect, is extremely subtle and difficult to detect in most circumstances. But if a void is large enough, and if it lies along our line of sight to a particular region of the cosmic microwave background, it could potentially create a detectable cold spot in the CMB. The larger and emptier the void, the stronger this effect would be. The integrated Sachs-Wolf effect is particularly important in a universe dominated by dark energy, like our own. Dark energy accelerates the expansion of the universe, causing gravitational wells to decay more rapidly than they would in a universe without dark energy. This amplifies the ISW effect, making it a valuable probe of dark energy's properties. However, the effect is still very small, typically causing temperature variations of only a few microkelvin, a tiny fraction of the primary anisotropies in the cosmic microwave background. In 2007, a team of astronomers led by Lawrence Rudnick, the same scientist who had identified the cold spot in the WMAP data, published a paper suggesting that they had found evidence for an enormous void in the direction of the cold spot. Using data from the NRAO VLA Sky Survey, which observed the sky in radio wavelengths, they identified a region in the constellation Eridanus that appeared to contain significantly fewer radio galaxies than expected. This region coincided with the location of the cold spot in the cosmic microwave background. The NRAO VLA Sky Survey, conducted with the Very Large Array Radio Telescope in New Mexico, had mapped the sky at a frequency of 1.4 GHz, detecting hundreds of thousands of radio sources, most of which were distant galaxies. When Rudnick and his colleagues analyzed the density of these radio sources across the sky, they found a significant underdensity in the direction of the cold spot. The number of radio galaxies in this region was about 40% lower than the average for other parts of the sky. Based on this underdensity of radio galaxies, Rudnick's team estimated the presence of a void approximately 1 billion light-years across, at a distance of about 8 billion light-years from Earth. If their analysis was correct, this would make it by far the largest known structure in the universe, dwarfing even the largest previously known voids by a factor of 2 or 3. To put this in perspective, recall that the typical cosmic void spans between 50 and 150 million light-years in diameter. The largest previously known void, the Boötes void, measures about 330 million light-years across. The supervoid suggested by Rudnick's analysis would be 3 times larger than the Boötes void, and perhaps 20 times the size of a typical void. It would be a cosmic structure of truly extraordinary scale. The void they identified appeared to be enormous, stretching nearly 1 billion light-years across. If confirmed, it would be the largest known structure in the universe, dwarfing even the largest previously known voids by a factor of 2 or 3. The discovery was met with both excitement and skepticism in the astronomical community. While it offered a potential explanation for the mysterious cold spot, a void of such immense size was difficult to reconcile with our understanding of how cosmic structure forms. The announcement of this potential supervoid generated considerable interest and controversy. Some astronomers were immediately skeptical, pointing out that the evidence from the Radio Galaxy Survey was relatively weak and that a void of this size would challenge our understanding of cosmic structure formation. Others were more open to the possibility, noting that the cold spot in the cosmic microwave background was itself an unexplained anomaly that might require extraordinary explanations. The discovery also sparked broader discussions about the nature of cosmic structure and the validity of the cosmological principle, a fundamental assumption in modern cosmology that the universe is homogeneous and isotropic on large scales. A structure as large as the purported supervoid would push the boundaries of what could be considered large-scale homogeneity, potentially challenging this principle. Several teams of astronomers set out to confirm or refute the existence of this supervoid. This was no simple task. To definitively identify a void, astronomers need to map the three-dimensional distribution of galaxies in a large volume of space. This requires not just measuring the positions of galaxies on the sky, but also determining their distances from Earth, which is much more challenging. Various techniques exist for estimating galactic distances, from measuring the redshift of their light, which increases with distance due to the expansion of the universe, to analyzing the properties of certain types of stars within them that have known intrinsic brightnesses. For several years, the evidence remained inconclusive. Some studies supported the existence of a large void in the direction of the cold spot, while others found no significant underdensity or challenged the methods used in previous analyses. The debate was complicated by the different observational techniques and datasets used by different research teams, each with its own strengths, limitations, and potential biases. The search for the supervoid took a significant turn in 2015 when a team led by Istvan Sapudi at the University of Hawaii published a paper in Monthly Notices of the Royal Astronomical Society. Using data from the Pan-Star Sown survey and the WISE satellite, they identified what they described as a supervoid aligned with the cold spot. This void, they estimated, was about 1.8 billion light-years across and centered at a distance of about 3 billion light-years from Earth. Sapudi's team used a technique called photometric redshift estimation to determine the approximate distances to millions of galaxies. This technique relies on observations through multiple color filters to estimate a galaxy's redshift, which is a measure of its distance. While less precise than spectroscopic redshift measurements, which analyze the specific wavelengths of light from a galaxy, photometric redshifts allow astronomers to efficiently estimate distances to many more galaxies. The void identified by Sapudi's team was not completely empty. Rather, it was a region where the density of galaxies was about 20% lower than the cosmic average. While this might not seem like a dramatic underdensity, it was spread across an enormous volume of space, making it one of the largest known structures in the universe. The team calculated that the probability of finding such a large void by chance was only about 1 in 20,000. Importantly, Sapudi's team also calculated the expected effect of this supervoid on the cosmic microwave background. Using models of the integrated Sachs-Wolfe effect, they estimated that the void could account for approximately 10% of the observed temperature decrement in the cold spot. This was a significant finding, as it suggested that the supervoid was indeed contributing to the cold spot, though it could not account for the entire anomaly. This conclusion presented a puzzle. If the supervoid was not sufficient to explain the cold spot, then what was causing the remaining 90% of the temperature decrement? Was it simply a statistical fluke in the cosmic microwave background itself, unrelated to the supervoid? Or was there some other physical mechanism at work, perhaps something not accounted for in the standard cosmological model? In 2017, a team led by Ruari Mackenzie at Durham University published a study that challenged the supervoid explanation. Using data from the Anglo-Australian Telescope, they conducted a spectroscopic survey of galaxies in the direction of the cold spot. Spectroscopic measurements provide more precise distance estimates than photometric ones, allowing for a more accurate, three-dimensional map of galaxy distribution. Mackenzie's team found no evidence for a single, large supervoid that could explain the cold spot. Instead, they detected several smaller voids and clusters along the line of sight, none of which was particularly exceptional on its own. They concluded that the structure of the universe in the direction of the cold spot was not significantly different from what would be expected in a random region of the sky. This study sparked a renewed debate about the nature of the supervoid and its role in creating the cold spot. Sapudi and his colleagues responded by arguing that their photometric survey, despite being less precise in individual galaxy distances, had measured many more galaxies and thus provided a more statistically robust measurement of the large-scale structure. They also suggested that the Mackenzie team's survey might not have been wide enough to fully encompass the supervoid. The debate was further complicated by different definitions of what constitutes a void in the cosmic web. Some astronomers define voids as regions completely devoid of galaxies, while others use a statistical definition based on the average density of the universe. By some definitions, a region with 20% fewer galaxies than average would not even qualify as a void, let alone a supervoid. In 2019, another comprehensive study by Seshadri Nadathur and his colleagues at the University of Portsmouth published a detailed analysis of the Planck data and galaxy surveys. They argued that the cold spot was likely a statistical fluke in the cosmic microwave background itself, rather than the result of a supervoid or any other intervening structure. According to their analysis, the probability of finding such a cold spot in a standard cosmological model, while low, was not low enough to rule out chance. Despite these conflicting results and interpretations, the search for the supervoid continued. Astronomers employed new observational techniques, more sophisticated statistical analyses, and improved theoretical models in an effort to resolve the mystery of the cold spot and the putative billion light-year void. One of the most comprehensive studies came in 2020, when a team led by András Kovács at the Institute of Astrophysics of the Canary Islands combined data from multiple surveys to create a detailed map of the galaxy distribution in the direction of the cold spot. Their analysis confirmed the existence of a large, underdense region, though its properties were somewhat different from what had been previously reported. Kovács and his team found that rather than a single, spherical void, the underdensity was more complex in shape and structure. It appeared to be elongated along our line of sight, like a cosmic tunnel stretching into the distance. The team also found that the underdensity was not uniformly empty, but contained smaller voids and filaments within it, creating a complex pattern of density variations. Most significantly, the team calculated that this structure could account for about 70% of the temperature decrement observed in the cold spot, a much higher fraction than previous estimates. While this still left some of the anomaly unexplained, it strengthened the case for the supervoid as a major contributor to the cold spot. The discovery of this vast cosmic structure raised profound questions about our understanding of the universe. If confirmed, a void of such immense size would challenge the standard model of cosmology, which predicts that structures larger than about 1.2 billion light-years should be extremely rare. The supervoid, stretching nearly 1.8 billion light-years according to some estimates, would be at the very limit of what is theoretically possible. Moreover, the coincidence of such a rare void with such a rare cold spot in the cosmic microwave background would itself be extraordinary. The probability of both occurring by chance in the same region of the sky would be vanishingly small. This coincidence suggested a causal connection between the two phenomena, yet the integrated Sachs-Wolf effect seemed insufficient to fully explain the relationship. As the debate continued, some astronomers began to consider more exotic explanations. Perhaps the standard cosmological model needed modification. Perhaps new physics was at play. Perhaps the cold spot and the supervoid were telling us something fundamental about the nature of our universe that we had yet to understand. The saga of the supervoid discovery illustrates the painstaking nature of modern cosmological research. From the initial detection of a subtle anomaly in the cosmic microwave background to the mapping of galaxy distributions across billions of light-years, each step required sophisticated instruments, careful analysis, and the collaborative efforts of scientists around the world. It also highlights the provisional nature of scientific knowledge. What began as a tentative identification of an unusual cold spot led to the discovery of what might be the largest structure in the universe. Yet even after years of research, the exact nature, size, and significance of the supervoid remain subjects of ongoing investigation and debate. As technology advances, new telescopes and surveys promise to shed further light on the supervoid mystery. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, will conduct the legacy survey of space and time, mapping billions of galaxies with unprecedented precision. The Nancy Grace Roman Space Telescope, also planned for launch in the coming decade, will provide a wide field view of the infrared universe, potentially revealing more details about the structure and contents of the supervoid. Whatever the ultimate resolution, the story of the supervoid discovery reminds us of the vastness and complexity of our universe. It reminds us that even in an age of precision cosmology, when we can measure the temperature of the universe's infant glow with exquisite accuracy and map the positions of millions of galaxies across billions of light-years, the cosmos still holds mysteries capable of challenging our most fundamental theories. And perhaps most poetically, it reminds us that sometimes it is not what is there, but what is not there, that proves most revealing. The absence of galaxies in the supervoid, like the absence of warmth in the cold spot, may ultimately provide the clues we need to better understand the nature of our universe. In the cosmic tapestry, the empty spaces may be as significant as the threads that we can see. To understand the significance of the billion light-year void, we must first understand what cosmic voids are and how they fit into the grand structure of our universe. Imagine our cosmos as an immense tapestry, woven not by human hands, but by the fundamental forces of physics over billions of years. This tapestry has a pattern, a structure that astronomers call the cosmic web. The cosmic web is the largest structure in existence. It began forming shortly after the Big Bang, when tiny fluctuations in the density of matter, quantum ripples in the newborn universe, began to grow under the influence of gravity. Regions that were slightly denser than average pulled in more and more matter, while regions that were slightly less dense lost matter to their surroundings. Over time, this process amplified these initial differences, creating a universe that is remarkably uneven in how its matter is distributed. Today, when we map out the positions of galaxies across vast regions of space, we see that they are arranged in a spectacular network. This network consists of several distinct components. There are galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. These clusters are the densest regions of the cosmic web, the knots where filaments converge. The filaments themselves are long, thread-like structures composed of galaxies and dark matter, stretching for hundreds of millions of light-years between clusters. These cosmic highways contain countless galaxies, often arranged like beads on a string. When several filaments come together, they can form what astronomers call walls or sheets, vast two-dimensional structures that contain many thousands of galaxies. And then there are the voids, the spaces between the filaments, clusters, and walls. These are regions where matter is unusually scarce, where galaxies are few and far between. They are the cosmic deserts, the empty spaces in our universe. Yet even these voids are not completely empty. They contain sparse populations of galaxies, often arranged along the boundaries of smaller voids within the larger void structure. Think of them as bubbles within bubbles, a hierarchy of emptiness extending across enormous distances. The typical cosmic void in our universe spans between 50 and 150 million light-years in diameter. To put this in perspective, recall that our Milky Way galaxy is approximately 100,000 light-years across. So a typical void could contain hundreds or even thousands of galaxies the size of our own, spaced far apart. These voids occupy about 80% of the volume of the universe, yet contain only about 20% of its galaxies. Most of the universe, in terms of volume, is relatively empty space. Voids form through a process astronomers call gravitational evolution. In the early universe, matter was distributed almost uniformly, with only tiny variations in density from place to place. Over time, gravity pulled matter away from regions that were slightly less dense than average. This matter flowed toward regions that were slightly more dense, amplifying the initial differences. The less dense regions became increasingly empty, while the denser regions grew increasingly crowded. This process continues even today, with voids growing larger and more pronounced as the universe ages. Inside a void, conditions are quite different from those in denser regions of the universe. The density of matter, both visible and dark, can be as little as 1/10 the cosmic average. This has profound effects on anything within the void. Galaxies form more slowly in these regions, as there is less material available for star formation. The few galaxies that do exist in voids tend to be smaller, bluer, and more isolated than those in denser environments. They often show evidence of ongoing star formation, appearing youthful compared to their counterparts in crowded regions. The gravity within a void is also weaker than in denser regions, which means that the expansion of space itself proceeds somewhat faster inside voids than outside them. This differential expansion causes voids to grow over time, not just because matter is flowing out of them, but because the space within them is stretching more rapidly than the space outside. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, all the dots move away from each other. But now imagine that some regions of the balloon are stretchier than others. These regions would expand more quickly, causing the dots within them to separate more rapidly. This is similar to what happens with voids in our universe. The space within them stretches more quickly than the space in denser regions, causing them to grow over cosmic time. This differential expansion of space has another interesting effect. The boundaries between voids and denser regions often become sites of intense galaxy formation and evolution. As matter flows out of voids and into filaments and walls, it collides with other matter, forming shock waves and turbulence that can trigger the collapse of gas clouds and the birth of new stars. Some of the most active regions of star formation in our universe occur along the edges of voids, where the emptiness meets the cosmic web. The voids themselves may seem like featureless expanses of emptiness, but they contain subtle structures of their own. Computer simulations and detailed observations have revealed that voids often contain tendrils of matter, gossamer filaments that pierce through the emptiness like spider webs in an abandoned room. These tendrils contain some of the most isolated galaxies in the universe, cosmic hermits that evolve in splendid solitude, far from the bustling interactions of their counterparts in denser environments. The largest voids discovered before the billion light-year supervoid were impressive in their own right. The Boötes void, discovered in 1981, spans about 330 million light-years and is one of the largest known voids in the nearby universe. The Sculptor void, another enormous cosmic bubble, measures about 200 million light-years across. These and other large voids were consistent with our understanding of how cosmic structure forms and evolves. They were at the upper end of what our models predicted, but not beyond the realm of possibility. Studying voids has become an important field in astronomy. By mapping their locations, sizes, and shapes, scientists can test theories about the formation and evolution of the cosmic web. Voids serve as natural laboratories where the properties of dark energy, the mysterious force driving the accelerating expansion of the universe, can be examined in relatively simple environments. They also provide insights into how galaxies evolve in isolation, free from the interactions and mergers that shape galaxies in denser regions. For most of astronomical history, these voids went unnoticed. Early astronomers, limited by the power of their telescopes, could see only the brightest and nearest objects in the night sky. It wasn't until the late 20th century, when astronomers began conducting large-scale surveys of galaxies, that the cosmic web became apparent. The first hints of vast empty regions appeared in the 1970s, but it was in the 1980s that voids were definitively discovered and recognized as fundamental components of cosmic structure. The discovery came when astronomers created a three-dimensional map of the distribution of galaxies in a large volume of space. They were surprised to find enormous empty regions, including the previously mentioned Boötes void. This region, spanning about 250 million light-years, was almost completely devoid of bright galaxies. The discovery of these large voids was a watershed moment in cosmology, providing clear evidence that the universe is organized into a complex web of structures on truly enormous scales. Since then, many more voids have been discovered, catalogued, and studied. The Sloan Digital Sky Survey, one of the most ambitious astronomical surveys ever undertaken, has mapped the three-dimensional positions of more than 1 million galaxies, revealing hundreds of voids of various sizes throughout the observable universe. Other surveys, using different wavelengths of light and different observational techniques, have added to our understanding of these cosmic empty spaces. The shapes of voids also tell us something about the nature of our universe. In a universe dominated by random motions, we would expect voids to be roughly spherical. But observations and simulations show that voids are often elongated, stretched into ellipsoidal, or even more complex shapes by the gravitational influence of surrounding structures. This elongation provides clues about the distribution of matter on the largest scales and the forces that have shaped cosmic structure over billions of years. Within the standard model of cosmology, known as lambda CDM, voids emerge naturally from the process of structure formation. This model combines the Big Bang theory with the presence of cold, dark matter, which interacts only through gravity, and dark energy, which drives the accelerating expansion of the universe. Computer simulations based on lambda CDM produce a cosmic web of filaments, clusters, and voids that closely matches what we observe in the real universe, at least up to certain scales. According to these simulations, the size distribution of voids should follow a predictable pattern. Small voids should be common, while larger voids should become increasingly rare. The probability of finding a void of a given size decreases exponentially as the size increases. This is similar to how, if you were to randomly place grains of sand on a table, you would find many small empty spaces, fewer medium-sized empty spaces, and very few large empty spaces. The largest voids predicted by lambda CDM should be around 300 to 400 million light-years across, which matches well with voids like the Boötes void. All of this brings us to an important point. Voids, while extraordinary in their emptiness, are not extraordinary in their existence. They are a normal, expected feature of our universe, predicted by our theories of how cosmic structure forms and evolves. What makes them interesting to astronomers is not that they exist, but rather their properties, their dynamics, and what they can tell us about the physics of our universe. So when astronomers discovered a void that was not tens or hundreds of millions of light-years across, but nearly 1 billion light-years in diameter, it raised eyebrows. A void of such immense size did not fit comfortably within our understanding of how cosmic structure should form. It was not just a void, but a supervoid, a cosmic emptiness of truly unprecedented scale. And its discovery would lead astronomers on a journey into one of the most perplexing mysteries of modern cosmology.